look to the stars and wonder what's out there. But imagine looking and seeing nothing. No planets, no neighbors, only us. Tonight, we imagine the unthinkable. What if Earth was the only planet in the universe? Imagine our pale blue home suspended in an endless void. The night sky filled only with distant stars, galaxies and nebulae, but no wandering points of light. No Mars glowing red in the evening sky. No brilliant Venus as the morning star. No majestic Jupiter with its family of moons. Just Earth, alone in the cosmic ocean. This solitude would reshape not just our understanding of the cosmos, but perhaps the very nature of our existence. How would life evolve on a world without a moon? Would human civilization develop differently without other planets to observe? Would we even look to the stars at all? Our universe is abundant with planets. Current estimates suggest there may be more planets than stars, perhaps trillions upon trillions throughout the cosmos. But tonight, we embark on a journey of imagination, a thought experiment that challenges our understanding of astronomy, physics, geology, biology, and even philosophy. What would it mean to be truly alone? Not just as a species, but as a planet. As the only solid world in an otherwise gaseous and ethereal universe, the implications stretch from the practical to the profound. Our planet's stability, its seasons, its tides, its very rotation might be fundamentally different. The history of life itself might follow paths we can barely conceive. As we drift through this meditation on cosmic solitude, we'll explore how Earth formed, how it might have evolved differently, and what it would mean for humanity to look up at a sky knowing we are the only world there is or ever will be. Let your mind wander through this alternate reality, a reality where Earth isn't just special or rare, but utterly unique, the only planetary body in existence. Picture yourself standing on a beach at night, waves gently lapping at your feet. You look up at the sky and there are only stars. No planets have ever existed. No moon circles our world. The ocean still moves with tides, but they are driven only by the sun, weaker and following different rhythms than those we know. When ancient peoples gazed upward in this solitary Earth, they would have seen only fixed points of light. No wanderers among the celestial sphere, no bright Venus cutting a path through the constellations, no red Mars changing position night after night, just the eternal, unchanging patterns of the stars themselves. Would astronomy have developed differently? Would we have understood gravity the same way? Would we have felt the same urge to reach beyond our world when there was nowhere to reach to? Consider for a moment how much of our understanding of the universe comes from studying our neighboring worlds. We learned about atmospheres by comparing Earth to Venus and Mars. We understood more about the history of impacts by looking at the Moon and Mercury. We discovered the possibility of subsurface oceans by studying Europa and Enceladus, moons of Jupiter and Saturn. All this knowledge would be missing in our lonely universe. And perhaps most profoundly, how would we think of ourselves? In a universe with only one planet, would we feel even more special and central to existence? Or would we feel like a cosmic accident, the only fluke of solid matter in a universe that otherwise made none? In our actual universe, we've been humbled repeatedly by science. We learned we're not at the center of the solar system. We learned our sun is just one of billions of stars in the Milky Way. We learned our galaxy is one of billions in the observable universe. And we've learned that planets are common, perhaps even the rule rather than the exception around stars. But in a universe with only Earth, we would be exceptional, unique, the only world where land meets sea, where mountains rise and fall, where canyons and valleys and plains stretch beneath an open sky, the only world where liquid water flows on the surface, the only world with ice caps and deserts, forests and meadows, rivers and lakes. We would also be the only place with life, the only home to bacteria and fungi, plants and animals, the only world with eyes to see the stars and minds to contemplate them, the only place where consciousness has arisen to wonder about its place in the cosmos. Would such uniqueness make us feel special, blessed, or would it create a profound loneliness? A sense that the universe is fundamentally inhospitable to worlds like ours, and we exist as some kind of aberration? These are the questions we'll explore tonight, as we journey through a cosmos where Earth stands alone. A universe where our world is not merely rare or precious, but truly one of a kind. The only planet that has ever been, or will ever be. Rest your thoughts as we begin this cosmic journey. A journey to understand our home by imagining it completely alone. A single island of rock and water in an endless sea of stars. What secrets would such a world hold? What beauty might it contain? And what would it tell us about our place in the actual universe we inhabit? Close your eyes and picture Earth, floating in darkness, the only planet in the universe. Our journey begins here. Before we erase all other planets from existence, let us appreciate the true cosmic abundance that surrounds us. Our actual universe teems with planetary bodies, from the familiar worlds of our solar system to the distant exoplanets circling other stars. Here in our celestial neighborhood, Earth is one of 8 major planets orbiting our Sun. Closest to our star is Mercury, a small cratered world of extreme temperatures where a day lasts 2 of its years. Next comes Venus, nearly Earth's twin in size but shrouded in thick clouds of sulfuric acid, its surface hot enough to melt lead. Then there is our Earth, the blue jewel, the third stone from the Sun. Beyond us orbits Mars, the red planet, with its rusty landscapes, ancient riverbeds, and polar ice caps. These 4 worlds make up what astronomers call the inner rocky planets, the terrestrial worlds. Beyond them lies the asteroid belt, a region filled with millions of rocky bodies, from dust-sized particles to the dwarf planet Ceres. And then we enter the realm of the giants. Jupiter, the king of planets, so massive that more than 1,000 Earths could fit inside it. A world of swirling storms and colorful bands of clouds, with a great red spot that has raged for centuries. A storm larger than our entire planet. Jupiter is attended by at least 79 moons, including 4 large worlds discovered by Galileo over 400 years ago. Saturn follows, famous for its magnificent rings that stretch tens of thousands of kilometers, yet are merely tens of meters thick. Saturn hosts a family of over 80 moons, including Titan with its thick atmosphere and methane lakes, and Enceladus with its subsurface ocean and erupting geysers. Uranus and Neptune stand as the ice giants, blue-green worlds of water, methane, and ammonia ices mixed with rock. Uranus rotates on its side, perhaps due to an ancient collision, while Neptune boasts the strongest winds in the solar system, reaching speeds of 2,000 kilometers per hour. Even beyond Neptune, we find the dwarf planets, including Pluto with its heart-shaped plains of nitrogen ice and its large moon Charon. And surrounding it all, stretching perhaps a quarter of the way to the nearest star, is the Oort Cloud, home to trillions of comets, frozen remnants from the birth of our solar system. But our cosmic neighborhood is just the beginning. When we gaze beyond our solar system, we discover that planets are the rule, not the exception. Since the first confirmed exoplanet discovery around a Sun-like star, in 1995, astronomers have identified over 5,000 planets orbiting other stars, with thousands more candidates awaiting confirmation. And these are merely the planets we can detect with current technology, a tiny fraction of what must exist. Extrapolating from these discoveries, scientists estimate our Milky Way galaxy alone may harbor hundreds of billions of planets, hundreds of billions of worlds, each with its own story, its own characteristics, its own place in the cosmic tapestry. Some of these exoplanets are familiar in scale, super-Earths that are somewhat larger than our world but still rocky, mini-Neptunes with thick atmospheres of hydrogen and helium. Some orbit their stars in just days or even hours. Others take centuries to complete a single year. We have found planets orbiting binary stars, worlds with 2 suns in their skies, like the fictional Tatooine from Star Wars. We have discovered planets orbiting the remnants of dead stars, pulsars that flash with clockwork precision. We have even detected planets floating freely between the stars, rogue worlds not bound to any stellar parent. There are planets with skies that rain molten glass sideways in hypersonic winds, like HD 189733b, planets with surfaces hot enough to vaporize rock where oceans are made of lava, planets where it might rain diamonds through thick layers of water and ammonia clouds. And there are worlds in the habitable zones of their stars, where temperatures might allow liquid water to exist on their surfaces, planets that, from a distance, might appear somewhat like our Earth. Planets are not merely common in our universe. They are essential to its structure and evolution. They form naturally from the disks of gas and dust that surround young stars. They help shape the architecture of their systems through their gravitational influences. They interact with their parent stars, with their sibling planets, with the smaller bodies that share their systems. And it's not just planets. Moons are abundant too. Our solar system alone contains over 200 natural satellites. Some are tiny captured asteroids. Others are worlds in their own right, with atmospheres, magnetic fields, subsurface oceans, active volcanoes or geysers erupting into space. Asteroids and comets number in the millions in our solar system and presumably exist in similar abundance around other stars. These smaller bodies represent the leftovers from planet formation, the pieces that never accreted into larger worlds, yet still play crucial roles in the evolution of planetary systems. Dwarf planets occupy a middle ground, substantial enough to pull themselves into spherical shapes under their own gravity, yet not massive enough to clear their orbital neighborhoods of other bodies. Pluto, Eris, Haumea, Makemake, Ceres, and likely many more yet undiscovered, represent this class of objects that blur the line between planet and asteroid. This, then, is our real universe, a cosmos brimming with worlds of all kinds, from gas giants to rocky planets, from ice worlds to lava planets, from moons to asteroids to comets. A universe where matter naturally gathers into planets around stars, where planetary systems are the norm rather than the exception. The night sky we see from Earth contains countless planets we cannot detect with our naked eyes. When we look at a star, chances are good that planets orbit it, invisible in the glare but present nonetheless. Our universe is a planetary universe, a cosmos where solid bodies are fundamental components of cosmic structure. But now, let us begin our thought experiment. What if all of this planetary abundance never existed? What if, instead of a universe teeming with worlds, there was only one? What if Earth alone represented the entirety of planetary existence? Imagine all the worlds we've just described simply vanishing: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all gone. The asteroid belt, empty. The Kuiper Belt, non-existent. The Oort Cloud, erased. All the moons, from our own lunar companion to the diverse satellites of the outer planets, disappeared as if they never were. And beyond our solar system, the same cosmic absence. No hot Jupiters racing around their stars in days. No super-Earths or mini-Neptunes. No potentially habitable worlds in their stars' Goldilocks zones. No rogue planets wandering the interstellar void. Just Earth. Alone in the vast emptiness. Our planet would still orbit the Sun, which would still be one among billions of stars in the Milky Way, which would still be one among billions of galaxies in the observable universe. But Earth would be unique in a way we can barely comprehend. The only place in the entire cosmos where matter had gathered into a planetary body. The stars would still shine. Galaxies would still form and evolve. Black holes would still bend space and time. Nebulae would still birth new stars. The cosmic web of dark matter would still shape the largest structures in the universe. But nowhere, in all this vastness, would there be another world like ours. No other planet of any kind, anywhere. Now, as we erase these trillions of worlds from existence, the void they leave behind creates space for our imagination. In this cosmic solitude, Earth's story would unfold very differently. Its birth, its evolution, its place in the universe would all be transformed by its singular nature. Let us journey now into this alternate reality. A universe with only one planet, Earth, the solitary world. In our universe, planets are born together, siblings emerging from the same parent cloud. To understand how Earth might exist as the only planet, we must first revisit how worlds normally come to be, and then imagine what cosmic circumstances might lead to a solitary birth. The story of every planet begins with a star. About 4.6 billion years ago, in a quiet arm of the Milky Way galaxy, a vast cloud of hydrogen, helium, and trace amounts of heavier elements began to collapse under its own gravity. As this nebula contracted, it began to spin, flattening into a disk with a dense center. The center grew hotter and denser until nuclear fusion ignited, and our sun was born. But the story doesn't end with the star. Surrounding the young sun was a swirling disk of gas and dust, the leftovers from the star's formation. Astronomers call this a protoplanetary disk, and it's from this material that planets emerge. Within this disk, tiny dust particles began to collide and stick together, forming pebbles, then rocks, then planetesimals hundreds of kilometers across. These larger bodies had enough gravitational pull to attract more material, growing larger still. The process accelerated as the bigger objects pulled in more matter, clearing their orbital paths. This is how planets normally form, a cosmic assembly line of ever larger objects emerging from the disk. In our solar system, this process gave birth to 8 planets, at least 5 dwarf planets, hundreds of moons, and countless smaller bodies. It's a natural progression from dust to worlds. But in our imagined universe, something extraordinary and unlikely must have happened, something that allowed Earth to form while preventing the birth of any other planet anywhere. What cosmic circumstances might lead to such an anomaly? One possibility is that the disk of material around our Sun was unusually small or depleted, containing just enough matter to form one Earth-sized planet, but nothing more. Perhaps a nearby supernova or a passing star disrupted the normal disk, stripping away most of the material before planets could fully form. Or perhaps the disk was fragmented and unstable, with only one region dense enough to give birth to a planet before the rest dissipated into space. In the chaotic early solar system, such unusual conditions are not impossible, merely highly improbable. Another possibility is that Earth was the sole survivor of a more typical planetary formation process. Perhaps other planets did begin to form, but through a series of catastrophic collisions, all the material eventually merged into one world, our Earth. Imagine a solar system where the early planetary bodies didn't settle into stable orbits, but instead gradually coalesced through repeated impacts until only Earth remained. This scenario would make Earth not just the only planet, but a composite world, containing within it the essence of what might have been many different planets. Our home would be the sum total of all planetary material in the solar system, a cosmic amalgamation. Yet another possibility is that Earth formed in the normal way, but some cosmic cataclysm later removed all other planets from existence. Perhaps a wandering star passed through our solar system, its gravity ejecting every world except Earth from orbit around the Sun. Or maybe some exotic phenomenon, beyond our current understanding of physics, selectively eliminated all planets except our own. But these scenarios only address our solar system. In our thought experiment, Earth is the only planet in the entire universe. For this to be true, the anomaly must extend beyond our local neighborhood to every star and every galaxy. Perhaps in this alternate reality, the laws of physics or the cosmic conditions simply do not favor planetary formation. Maybe the fundamental constants of nature differ slightly from our universe, making it extraordinarily difficult for dust to aggregate into worlds. Earth's existence becomes not just unusual, but miraculous, a cosmic exception to the rule that matter remains diffuse. In such a universe, stars would still form, but their protoplanetary disks would typically dissipate before planets could coalesce. The interstellar medium might contain abundant dust, but lack the conditions necessary for that dust to gather into larger bodies. Comets, asteroids, planetesimals, all would be virtually non-existent throughout the cosmos. This raises an intriguing question. If planetary formation is so cosmically disfavored, how did Earth come to be at all? Perhaps our world represents a perfect storm of unlikely conditions, a rare conjunction of factors that, just once in the entire history of the universe, allowed enough material to gather in one place long enough to form a planet. Maybe Earth formed through some process entirely different from normal planetary accretion. Perhaps it condensed directly from an unusually dense knot in the primordial nebula, bypassing the usual stages of planetesimal formation. Or maybe it represents the core of a failed star, a body that began to form as a brown dwarf, but never gathered enough mass to sustain any kind of fusion. Whatever the mechanism, Earth's birth in this solitary universe would be an event of cosmic singularity. Not merely rare or unusual, but unique in the entire history of existence. The only time and place where matter gathered into a planetary body. Such cosmic uniqueness would have profound implications for Earth's composition and structure. In our actual universe, Earth contains a specific mix of elements determined by where and how it formed in the solar nebula. The inner planets are rocky because the early solar system was hot near the Sun, preventing volatile materials like water and light gases from condensing. The outer planets are gaseous because they formed beyond the frost line, where it was cold enough for ices to remain solid. But in a universe where Earth is the only planet, this compositional gradient wouldn't necessarily apply. Earth might contain a different mix of elements, perhaps incorporating materials that in our universe only exist in the outer solar system. Or it might be depleted in certain elements that in our reality were delivered by asteroid and comet impacts after the planet's initial formation. The internal structure of this solitary Earth might also differ. Our actual planet has a differentiated interior, with a dense iron core surrounded by a mantle of silicate rocks and a relatively thin crust. This structure emerged partly through gravitational sorting during Earth's molten early phase, but also through impacts with other bodies that added material and energy to the young planet. Without these impacts, without the complex gravitational interactions with other planets, would Earth's internal organization be the same? Would it still have the layered structure that, in our world, ultimately gave rise to the magnetic field that protects our atmosphere from solar radiation? Speaking of atmospheres, Earth's air in this solitary universe might be dramatically different as well. In our reality, Earth's modern atmosphere is not its original one. The primordial atmosphere was likely dominated by gases from volcanic eruptions and impacts, rich in carbon dioxide, water vapor, nitrogen, and sulfur compounds. The oxygen that now makes up about 21% of our air came later, a biological product from photosynthetic organisms. But the composition of that early atmosphere was influenced by materials delivered by comets and asteroids, bodies that in our solitary universe might never have existed. Would this Earth still have received the same volatile compounds? Would its atmosphere have evolved along a similar path? And what of Earth's water? In our universe, there's ongoing debate about the origin of Earth's oceans. Some of our water was likely incorporated during the planet's formation, but significant amounts may have been delivered later by water-rich asteroids and comets. If these smaller bodies never existed in our imagined cosmos, would Earth still be a blue planet? Or would it be a drier world, with smaller, shallower seas, or perhaps no surface water at all? The timing of Earth's formation might also differ in this solitary universe. In our reality, astronomers believe the solar system's planets formed within about 100 million years after the Sun's birth. This timeline was influenced by the complex gravitational interactions of many growing planetary bodies, all competing for material from the disk. But in a system where only one planet was forming, with no competition for resources and no gravitational perturbations from other bodies, would Earth have formed faster, or perhaps slower, lacking the accelerating effects of nearby massive objects pulling in additional material? The Earth we know has a relatively circular orbit around the Sun, a characteristic it shares with most of the other planets in our solar system. This circularity is the result of billions of years of gravitational interactions that gradually stabilize the orbits of surviving planetary bodies. But in a solar system where Earth formed alone, what would determine the shape of its orbit? Without the gravitational influence of Jupiter and the other planets, Earth's path around the Sun might be more elliptical, leading to greater seasonal variations as its distance from the Sun changed more dramatically throughout its year. Perhaps most significantly, a solitary Earth would likely have no moon. In our universe, the moon is thought to have formed when a Mars-sized body collided with the early Earth, ejecting a ring of debris that eventually coalesced into our lunar companion. But in a universe where Earth is the only planet, where would this impactor have come from? Without a moon, Earth's evolution would take a dramatically different course. The moon stabilizes Earth's axial tilt, preventing wild swings in our orientation relative to the Sun. These swings would cause extreme climate variations that would make the development of complex life far more challenging. The moon also slows Earth's rotation through tidal forces, gradually lengthening our days from just hours in the early Earth to the 24 hours we experience now. A moonless Earth might spin faster, might wobble chaotically on its axis, might experience minimal tides driven only by the Sun. All these differences would reshape the history of our planet in profound ways. If Earth truly stood alone in the universe, its gravitational interactions would be limited to its star and to its own internal dynamics. There would be no planetary alignments, no gravitational assists, no complex dance of resonances and perturbations that, in our universe, helps determine the long-term stability of the solar system. Would such simplicity make Earth's orbit more stable over cosmic time? Or would the lack of a complex gravitational web actually introduce more chaos into the system without the balancing effects that multiple bodies can provide? And what of the Sun itself? In our universe, the Sun's evolution is subtly influenced by the gravitational pull of the planets, especially massive Jupiter. While these effects are small compared to the Sun's internal dynamics, they do exist. In a universe where Earth is the only planet, the Sun would evolve according to purely stellar physics, without even these minor planetary tugs. As we imagine the birth and early evolution of this solitary Earth, we must recognize that its uniqueness extends beyond mere rarity. In a universe where planets simply don't form as a rule, Earth's existence represents a fundamental anomaly, a cosmic exception that defies the prevailing conditions of reality. Such a world would truly be born of stardust, the only place in all the cosmos where the debris of stellar evolution gathered into a solid, differentiated body capable of supporting oceans, atmospheres, and potentially life. A singular jewel in an otherwise gaseous and diffuse universe. In this cosmic abnormality, Earth takes on a significance that transcends even its status in our actual universe. Here, it's not merely special as the only known life-bearing world. It becomes metaphysically unique, the only instance where the universe's matter organized itself into planetary form at all. The birth of a solitary planet, the only one in the entire cosmos, would truly be a remarkable event. An impossible singularity in a universe otherwise devoid of worlds. Earth, alone in the cosmic arena, a lone solid sphere orbiting an ordinary star in an ordinary galaxy, yet extraordinary in its very existence. In this lonely universe, Earth forms by chance, a cosmic accident in a silent cloud. The only planet that ever was or ever will be. In our real universe, Earth dances with a partner. Our moon, a quarter the diameter of our planet, orbits us in a cosmic ballet that has continued for over 4 billion years. This dance has shaped our world in ways both obvious and subtle, influencing everything from our oceans to our days, to the very stability of life itself. But in our imagined universe of solitude, this dance never began. Earth waltzes alone around the Sun, without its faithful companion. Let us contemplate what this moonless existence would mean for our planet. When you stand at the seashore and watch the tides come in and recede, you are witnessing the moon's gravitational embrace of Earth. The moon's pull creates a bulge in our oceans, both toward and away from the lunar position. As Earth rotates beneath these bulges, coastlines experience the rhythmic rise and fall of water that we call tides. The Sun also contributes to tides, but its influence is less than half that of the moon, despite its vastly greater mass. This is because tidal force depends not just on the mass of the body creating it, but on how quickly that gravitational pull changes across the diameter of Earth. The Sun is so distant that its gravitational gradient across our planet is relatively small, while the much closer moon creates a steeper gradient. In a world without a moon, tides would still exist, but they would be generated solely by the Sun. These solar tides would be less than half as strong as our familiar lunar-dominated tides. Coastlines would still experience rising and falling waters, but the difference between high and low tide would be much less dramatic. Tidal ranges that in our world measure several meters might be reduced to less than a meter in many locations. These diminished tides would have profound implications for coastal ecosystems. Tidal pools, those remarkable microhabitats that are alternately submerged and exposed, would be less extensive. The intertidal zones, where land and sea intermingle, would narrow. Species that have evolved to thrive in these shifting environments might never have developed their specialized adaptations. The reduced tidal flow would also affect how oceans mix. In our world, tidal forces create currents that help circulate nutrients and oxygen, supporting marine ecosystems. Without the moon's influence, ocean circulation patterns would differ, potentially leading to less productive seas. But the absence of the moon would change far more than just our tides. Consider the length of Earth's day. When Earth first formed, it likely rotated much faster than it does now, with days perhaps as short as 6 to 8 hours. Over billions of years, the moon's gravitational pull has created a drag that gradually slowed our planet's spin, lengthening our days to their current 24 hours. Without a moon, a solitary Earth might still be spinning much more rapidly. Days could be just 10 to 12 hours long rather than 24. This faster rotation would create stronger Coriolis effects, changing global wind patterns and ocean currents. Weather systems would move differently across the face of the planet. Hurricanes and cyclones might be more frequent or more intense. The climate itself would be reshaped by this rapid spin. Perhaps most importantly, the Moon has acted as a stabilizing influence on Earth's axial tilt, what scientists call our obliquity. Earth is tilted about 23.5 degrees relative to its orbital plane, and this tilt gives us our seasons. Without the Moon's gravitational influence, computer models suggest Earth's tilt would vary chaotically over time, potentially swinging from 0 degrees to over 40 degrees over periods of just millions of years, a mere blink in geological time. Imagine an Earth whose axial tilt gradually shifts from 0 to 45 degrees and back again every few million years. At 0 degrees, there would be no seasons at all. Every day of the year would receive the same amount of sunlight at any given latitude. The equator would be hot year-round, the poles cold year-round, with no annual cycle of warming and cooling. Then, as the planet's tilt gradually increased, seasons would emerge and grow more extreme. At a tilt of 45 degrees, seasons would be severe beyond anything we know in our world. During summer, the high latitudes would experience constant daylight with the sun high in the sky, creating extraordinary heating. During winter, those same regions would be plunged into months of frigid darkness. Such wild swings in seasonality would create enormous challenges for life. Species would face intense, selective pressure to adapt to constantly changing conditions. Ecosystems would be repeatedly disrupted as the climate regime transformed every few million years. The evolution of life would likely take very different paths than it has in our more stable world. Even Earth's climate stability on shorter timescales would be affected. The Moon's gravitational interactions help moderate some of Earth's orbital variations, contributing to the relative climate stability that has characterized much of our planet's history. Without this moderating influence, Earth's climate might oscillate more dramatically between warm and cool periods, creating additional challenges for developing life. Let us also consider Earth's magnetic field, the invisible shield that protects our atmosphere from the solar wind. This field is generated by the movement of molten iron in Earth's outer core, a process driven partly by our planet's rotation. If a moonless Earth spun significantly faster, this could alter the dynamics of the core, potentially creating a stronger magnetic field. A stronger magnetic field might offer better protection against solar radiation, which could be beneficial for surface life. However, it might also interact differently with charged particles from the Sun, creating more frequent and intense auroras and potentially affecting Earth's upper atmosphere in ways that would influence climate. The absence of a moon would also change Earth's appearance from space. There would be no moonlight illuminating the night landscape, no lunar reflections dancing on the water. Nights would be darker, lit only by the stars, and perhaps the faint luminescence of the Milky Way. For early humans or their evolutionary counterparts, if they emerged in this world, navigation after sunset would be more challenging without the moon's helpful glow. Beyond the physical and biological implications, the absence of the moon would profoundly affect human culture, assuming humanity evolved on this solitary world. So much of our art, music, mythology, and literature draws inspiration from the moon. Its phases have helped mark time for countless civilizations. Its eclipses have stirred wonder and sometimes fear. Its light has guided travelers for millennia. Without the moon, our calendars might be different, perhaps based solely on solar cycles rather than the lunar months many cultures have used. Our conception of time and its passage might have developed along different lines. Even our language would lack the many moon-inspired words and metaphors we take for granted. For early astronomers, the absence of the moon would remove a crucial stepping stone to understanding the cosmos. The moon was humanity's first celestial exploration target, the only other world whose surface details could be observed with the naked eye or simple telescopes. Without this accessible astronomical laboratory, our development of planetary science might have progressed differently, perhaps more slowly. But let us return to the physical implications of a moonless Earth, particularly regarding our planet's formation history. In our universe, the moon was born from a catastrophic collision between the young Earth and a Mars-sized body astronomers call Theia. This massive impact did more than just create the moon. It also substantially altered Earth itself. The collision with Theia likely added significant mass to Earth, perhaps as much as 10% of our planet's final size. This material would be missing from a solitary Earth that never experienced such an impact, potentially making our world somewhat smaller. This ancient impact also appears to have delivered substantial rotational energy to the Earth-Moon system. Without this energetic kick, a solitary Earth might spin more slowly than our model suggests, potentially counteracting the effect of not having the Moon's tidal drag to slow rotation over time. The precise rotational state of this alternative Earth is difficult to predict with certainty. The giant impact that formed our Moon also substantially altered Earth's composition. The collision likely stripped away some of Earth's original mantle, possibly including much of its lighter elements. This material later formed the Moon, which is notably depleted in iron compared to Earth, suggesting it formed primarily from the mantle of both bodies rather than their cores. A solitary Earth that never experienced this impact might have a different composition, with a different ratio of core to mantle material. This could affect everything from its internal structure to its surface chemistry to its ability to generate a magnetic field. The impact that created the Moon also likely delivered significant heat to the young Earth, perhaps even melting the entire planet temporarily. This global magma ocean would have allowed heavy elements to sink toward the center, while lighter materials floated toward the surface, enhancing the differentiation of Earth's layers. Without this melting event, a solitary Earth might be less internally differentiated, with implications for its geological evolution. Some scientists have even suggested that the Moon-forming impact helped establish the conditions necessary for plate tectonics on Earth. Without the Moon and the circumstances of its creation, would our solitary Earth still have developed the dynamic crustal movements that shape our continents and drive our long-term carbon cycle? If not, the planet's ability to regulate its climate over geological timescales might be compromised. Let us also consider the implications for Earth's oceans. In our world, the Moon's gravitational pull creates not just tides but also tidal heating, a slight warming effect from the constant flexing of Earth's solid body. While this heating is modest compared to other energy sources on Earth, it may have played a role in Earth's early evolution, perhaps contributing to maintaining liquid water oceans during periods when the young sun was less bright than today. Without the Moon's tidal heating, a solitary Earth might have been more vulnerable to freezing during the faint young sun period of Earth's history, when solar luminosity was up to 30% lower than present levels. This could have made the emergence of life more difficult or delayed its appearance. The Moon also influences Earth's orbital dynamics in subtle ways. The Earth-Moon system orbits around a common center of mass, or barycenter, located about 4,700 kilometers from Earth's center, within the body of our planet, but off-center. This creates a slight wobble in Earth's orbit that wouldn't exist for a solitary Earth. Without this wobble, Earth's orbital properties might evolve differently over long timescales. The precise implications are difficult to predict, but they could include changes to the Milankovitch cycles, the periodic variations in Earth's orbit, and axial tilt that influence our long-term climate patterns, and have contributed to the rhythm of ice ages during recent geological history. Beyond all these physical effects, there are biological considerations that reach to the very foundations of life on Earth. Some researchers have suggested that the Moon's creation shaped the conditions that made life possible on our planet. The giant impact may have delivered key volatile elements or created the pressure and temperature conditions that allowed certain critical prebiotic chemistry to occur. It's even been proposed that the cycle of tides created by the Moon provided unique environments for the development of early life. Tidal pools, regularly filled and emptied, create a natural laboratory where chemicals can concentrate, interact, and be exposed to different conditions in a cyclical pattern. These cycling conditions might have facilitated the complex chemistry that eventually led to the first self-replicating molecules. Without the Moon and its tides, would life have emerged on Earth at all? Or would it have taken a different form, emerged at a different time, or followed a different evolutionary path? These questions highlight how profoundly the Moon has shaped not just Earth's physical characteristics, but potentially the very existence of life as we know it. In our moonless, solitary Earth, Nights would pass without the silver illumination we know so well. No lunar phases would mark the passage of weeks. No eclipses would momentarily darken the sun or turn the moon blood red. The sky would host only the distant stars, the wandering point of Venus as morning or evening star, and perhaps the faint band of the Milky Way stretching across dark skies untainted by moonlight. The rhythms of life would be different, driven solely by the daily rotation of Earth and its annual journey around the sun, without the intermediate cycle of the lunar month that has influenced so many biological patterns. Species that in our world synchronize their reproduction with the lunar cycle, from coral spawning to sea turtles nesting, would instead respond to different cues or develop different reproductive strategies entirely. For a solitary Earth without a moon, the very notion of balance takes on new meaning. The physical balance of axial stability would be missing, creating a world of more extreme contrasts and changes. The temporal balance of daily, monthly, and yearly rhythms would be altered, with only the solar day and year marking time's passage. The ecological balance of species adapted to tidal zones and lunar cycles would be replaced by different adaptations to different conditions. Yet life, resourceful and adaptive, would likely still find a way to emerge and thrive on this solitary world. Different perhaps from the life we know, following different evolutionary paths to meet different challenges, but the fundamental drive to exist, to reproduce, to adapt and change would remain, finding expression in forms suited to this moonless Earth. As we contemplate this alternative reality, we gain a deeper appreciation for the cosmic partnership that has shaped our actual world. The moon, so often taken for granted as merely a beautiful object in our night sky, reveals itself as an architect of Earth's habitability, a silent partner in creating the conditions that allowed us to exist. In this lonely universe, Earth forms in isolation, without the catastrophic collision that gave birth to the moon. Its axis wobbles chaotically through time. Its spin remains rapid. Its tides rise and fall with gentle subtlety under the sun's distant pull. Its nights are darker. Its oceans mix differently. Its climate shifts more dramatically over geological time. Even one missing companion changes everything, and here there are none. In our solitary universe, our sun would be a parent with just one child. A stellar presence surrounded not by a family of worlds, but by a single planetary offspring. This cosmic singularity would reshape not just Earth's development, but the very nature of our star and its evolution through time. Stars are born in stellar nurseries, vast clouds of gas and dust that collapse under their own gravity. As a protostar forms at the center of such a collapsing cloud, the remaining material typically flattens into a disk surrounding the young star. It is from this protoplanetary disk that a family of planets usually emerges. In our actual universe, this process is remarkably consistent. Observations of young stars reveal that nearly all of them are surrounded by such disks early in their lives. These structures contain all the raw materials needed for planet formation, from rocky silicates to ices to organic compounds. Over time, these materials coalesce into planetesimals and eventually full-fledged planets, creating the rich diversity of worlds we observe around other stars. But in our imagined universe, this pattern is broken. The sun forms. A protoplanetary disk likely still surrounds it initially, but somehow, against all cosmic odds, only Earth coalesces from this disk. No other planets, no asteroid belt, no cometary cloud. Just one solitary world, orbiting alone in the emptiness. What would such uniqueness mean for our star? In physical terms, the absence of other planets would simplify the sun's gravitational environment. In our actual solar system, the sun's motion is influenced slightly by the gravitational pull of the planets, particularly massive Jupiter. The entire solar system orbits around a common center of mass, or barycenter, which lies sometimes within the sun and sometimes just outside its surface, depending on the positions of the planets. This creates a subtle wobble in the sun's position. Astronomers use this very wobble to detect exoplanets around other stars, measuring how a star's slight movements betray the gravitational influence of orbiting worlds. In our solitary system, the sun's movement would be much simpler. The barycenter of the Sun-Earth system would lie well within the sun itself, about 500 kilometers from the sun's center. This is less than 1/1000th of the sun's radius. The star would still wobble slightly due to Earth's gravitational pull, but this wobble would be minimal compared to the complex motion created by a full planetary system. This simplified orbital dynamics might seem inconsequential, but over billions of years, even subtle differences can compound. The Sun's rotation might evolve differently without the angular momentum exchanges that occur with multiple planets. Its magnetic field generation might follow a slightly different pattern, perhaps altering the frequency or intensity of solar flares and coronal mass ejections. Beyond these mechanical considerations, there's the matter of the Sun's composition. In our universe, the planets and the Sun formed from the same nebular material, but the proportions of elements differ between them. The Sun captured the majority of the light gases, like hydrogen and helium, while the planets incorporated higher percentages of heavier elements. In a universe where Earth is the only planet, the distribution of elements would be different. All the material that in our reality went into forming Mercury, Venus, Mars, and the outer planets would have either been incorporated into the Sun, blown away into interstellar space, or perhaps some small fraction might have been added to Earth. This would likely make the Sun slightly richer in heavier elements, what astronomers call metals, although the difference would be minimal, given that the planets collectively contain less than 0.1% of the solar system's total mass. Still, even small changes in stellar composition can influence a star's evolution, potentially altering its luminosity or lifespan by modest amounts. The Sun's early evolution might also have differed in this solitary system. Young stars often undergo a phase of intense activity, with powerful flares and significant mass loss through stellar winds. These energetic outbursts interact with the protoplanetary disk and the forming planets, potentially stripping away atmospheres or altering chemical compositions. With only Earth to interact with these solar tantrums, the pattern of early solar evolution might have taken a slightly different course. Perhaps the Sun would have retained a bit more of its mass without other planets and their magnetic fields interacting with its outflows. Or maybe the solar wind would have shaped Earth's early atmosphere differently without other planetary bodies to share its impact. One intriguing aspect of a Sun with no other planets concerns the early migration of worlds that likely occurred in our solar system. Astronomical evidence suggests that the giant planets of our system didn't form where they currently reside. Instead, they migrated, moving inward or outward from their birthplaces due to interactions with the disk and with each other. These migrations would have influenced Earth's formation and early history. Jupiter's inward migration may have limited Mars's growth, while also delivering water-bearing asteroids to the inner solar system. The complex dance of the giant planets likely shaped the architecture of the entire system, including Earth's final form and composition. In our solitary system, none of these migrations would occur. Earth would form and evolve without these external influences, potentially resulting in a somewhat different world than the one we inhabit. Its size, composition, and orbit might all reflect the absence of these planetary interactions. Another consideration is the Sun's long-term stability. In our universe, the gravitational influences of the planets, while small, help maintain the Sun's relatively steady behavior over astronomical timescales. The resonances and rhythms of a multi-planet system create a kind of celestial harmony, a balance that helps preserve the overall structure. Without this complex gravitational web, would the Sun's behavior be more or less stable? The answer isn't straightforward. On one hand, fewer gravitational interactions might mean fewer perturbations to the Sun's equilibrium. On the other hand, the distributed mass of multiple planets provides a kind of inertia to the system, a resistance to change that might be reduced in a solitary system. Let us also consider the Sun's light, the radiant energy that bathes Earth and makes life possible. In our actual universe, the planets collectively reflect some of the Sun's light back into space, a phenomenon astronomers call albedo. Jupiter alone reflects a significant amount of sunlight back toward the inner solar system. In a universe with only Earth, this planetary reflection would be absent. The only light returning to the Sun would be the modest amount reflected by Earth, and whatever dust might exist in the system. Would this make any difference to the Sun itself? Probably not in any meaningful way, given that the planets reflect only a tiny fraction of the Sun's total output. But it represents another subtle difference in how energy flows through this simplified system. From Earth's perspective, the Sun would appear much as it does in our reality. Same size, same brightness, same color. The solar spectrum, the specific wavelengths of light it emits, might be very slightly different if its composition varied, but not in any way visible to the naked eye. However, solar eclipses would not exist in this moonless world. One of the most spectacular celestial phenomena we experience, the perfect alignment of Sun, Moon, and Earth that temporarily turns day to night, would never occur. The Sun would shine uninterrupted except for occasional transits of Earth's clouds, or perhaps very rarely, passages of interstellar dust clouds. Without solar eclipses, humanity might have taken longer to develop certain aspects of astronomy. These events have historically provided unique opportunities to study the Sun's outer atmosphere, the corona, visible only when the blinding solar disk is completely blocked. This has led to important discoveries about the nature of our star. In a world without eclipses, such knowledge might have been delayed. Let us now consider the Sun's magnetic activity and its effects on Earth. Our star possesses a complex magnetic field that reverses polarity approximately every 11 years, creating the solar cycle of sunspots, flares, and coronal mass ejections. This magnetic behavior is driven by the dynamics of plasma within the Sun, particularly the differential rotation between its equator and poles. Would a Sun with no other planets exhibit the same magnetic behavior? Most likely yes, as the solar magnetic cycle is primarily driven by internal processes rather than external influences. However, there might be subtle differences. The absence of planetary tidal forces, particularly those from massive Jupiter, might alter the Sun's rotation slightly over billions of years, potentially affecting its magnetic dynamo. For Earth, changes in solar magnetic activity could have significant implications. The solar wind, a stream of charged particles flowing outward from the Sun, interacts with Earth's magnetic field, creating space weather phenomena like auroras and potentially affecting our planet's upper atmosphere. If the Sun's magnetic behavior were even slightly different in this solitary system, it might alter the frequency or intensity of solar storms. This could affect everything from the development of life, which must contend with radiation, to the long-term evolution of Earth's atmosphere, which can be eroded by particularly intense solar activity. Beyond the physical interactions between the Sun and Earth, there are the more abstract considerations of what it means for a star to have just one planet. Stars are typically not solitary objects but centers of systems, with planets forming as a natural byproduct of stellar birth. A Sun with only one world represents a kind of cosmic abnormality, a break in the pattern we observe throughout the universe. In such a unique arrangement, the relationship between star and planet takes on a different character. Instead of being one member of a diverse planetary family, Earth becomes the Sun's sole companion, the only solid body orbiting in an otherwise empty system. The Sun shines not on a collection of worlds, but on a single, solitary sphere. This uniqueness might not matter in physical terms, but from a philosophical perspective, it transforms the Sun from the center of a system to one half of a cosmic partnership, star and planet, locked in an eternal dance with no other participants. The absence of other planets would also change how the Sun interacts with the broader galaxy. In our universe, the Sun and its planets move through the Milky Way together, occasionally passing near other stars. During these stellar encounters, the outer planets and especially the distant Oort Cloud can be gravitationally disturbed, sometimes sending comets toward the inner solar system. In a universe with only Earth, close encounters with other stars would have different consequences. Without an Oort Cloud or outer planets to be perturbed, stellar flybys would mainly affect the Sun-Earth system directly. If a passing star came close enough, it might alter Earth's orbit, or even eject our planet from the Sun's embrace entirely, though such close approaches are extremely rare. The Sun's journey through the galaxy would also be slightly different without the momentum of multiple planets. The difference would be minuscule given that the planets contain so little of the system's total mass, but over billions of years, even tiny variations can lead to divergent paths. Perhaps in this solitary system, the Sun would follow a slightly different orbit around the galactic center, encountering different regions of the Milky Way than in our reality. Let us also consider the Sun's ultimate fate. In about 5 billion years, our star will exhaust the hydrogen fuel in its core and begin to expand into a red giant. In our universe, this expansion will engulf Mercury and Venus, and possibly Earth, depending on how much mass the Sun loses through stellar winds before reaching our orbit. In a universe with only Earth, the Sun's evolution would likely follow the same basic path. However, subtle differences in composition or rotation might slightly alter the timeline or the extent of the red giant phase. Earth's fate in this distant future might be marginally different, perhaps facing the solar furnace slightly sooner or later than in our reality. After the red giant phase, the Sun will shed its outer layers, creating a planetary nebula, while its core collapses into a white dwarf star. This stellar remnant will slowly cool over trillions of years, eventually fading to a black dwarf. In our universe, the outer planets will likely survive this transformation, continuing to orbit the stellar corpse like mourners circling a grave. But in our solitary system, if Earth is consumed during the red giant phase, the Sun's death will leave nothing behind but the white dwarf itself, truly alone in the emptiness of space. No planetary companions will remain to bear witness to its long, slow cooling. The cosmic partnership of Sun and Earth will have come to its final end. As we contemplate a Sun with no other planetary children, we gain a deeper appreciation for the complex interrelationships that define our actual solar system. The Sun is not merely a source of light and heat, but a gravitational anchor, a magnetic influence, and a member of a dynamic system where each component, from tiny Mercury to massive Jupiter, plays a role in the whole. In our imagined universe, the Sun loses this rich context. It becomes simpler in some ways, but perhaps poorer in others. A star without a proper system, a parent with just one child instead of a diverse family, a single star, a single planet, no orbits to interact, no dance, just a silent spin. Our Earth bears the scars of its violent past. Crater lakes dot our landscapes. Impact basins lie hidden beneath forests and fields. The very composition of our planet has been shaped by countless collisions with visitors from space, from microscopic dust to mountain-sized boulders. But in our imagined universe, where Earth stands alone, this cosmic bombardment would never have occurred. No asteroids, no comets, no impacts to reshape the surface of our world. What would it mean for Earth to have developed in pristine isolation, never struck by objects from beyond? In our actual solar system, asteroids and comets represent the leftovers of planetary formation. The asteroid belt between Mars and Jupiter contains millions of rocky bodies that never accreted into a planet. The Kuiper Belt beyond Neptune hosts icy objects that similarly failed to combine into larger worlds. And the distant Oort Cloud, extending halfway to the nearest star, contains trillions of cometary nuclei, frozen relics from the solar system's birth. These smaller bodies have played crucial roles in Earth's history. They are not merely debris, but active participants in the evolution of our planet and the life it hosts. Their absence in our solitary universe would profoundly alter Earth's development in ways both obvious and subtle. Consider the late heavy bombardment, a period approximately 4 billion years ago, when the inner solar system experienced an intense barrage of impacts. During this cataclysmic era, countless large objects struck Earth, reshaping its surface and potentially delivering essential materials. Some theories suggest that much of Earth's water arrived during this time, carried by water-rich comets and asteroids from the outer solar system. Without this bombardment, would Earth still have its vast oceans? Or would it be a drier world, with smaller seas, or perhaps no surface water at all? The evidence for water delivery remains debated among scientists, with some research suggesting Earth's oceans formed primarily from water incorporated during the planet's formation. But even if Earth retained some of its original water, the bombardment likely added to this inventory and certainly influenced how water was distributed. Beyond water, impacts delivered other crucial materials to early Earth. Carbon compounds, the building blocks of life, may have arrived aboard meteorites. Precious metals like gold and platinum, which sank to Earth's core during its molten formation, were replenished in the crust by subsequent impacts. Iron and nickel from metallic asteroids became incorporated into Earth's composition. Without this cosmic delivery service, Earth's chemistry would differ in subtle but significant ways. Certain elements might be less abundant in the crust. The distribution of minerals might follow different patterns. The raw materials available for life's emergence might be more limited or differently composed. The physical structure of Earth would also differ without impact events. Each major collision reshaped our planet's surface, creating craters, basins, and in the most extreme cases, potentially altering the planet's rotation or axial tilt. The energy delivered by impacts melted rock, vaporized oceans, and triggered volcanic eruptions that further modified Earth's geology. In our imagined universe, Earth's surface would evolve solely through internal processes like plate tectonics, volcanism, and erosion, without the sudden, dramatic restructuring caused by cosmic impacts. The landscape would develop more gradually, more predictably, following the steady rhythms of internal geologic forces rather than the random punctuations of extraterrestrial collisions. Perhaps most significantly, the absence of impacts would change the story of life on Earth. Major impact events have repeatedly altered the course of evolution by causing mass extinctions that cleared ecological niches and allowed new species to flourish. The most famous of these, the Chicxulub impact that contributed to the extinction of the dinosaurs 66 million years ago, created the opportunity for mammals to diversify and eventually give rise to humans. Without such reset events, evolution might follow more continuous paths, with dominant species remaining in place for longer periods and fewer opportunities for dramatic diversification. The history of life might unfold more gradually, with fewer revolutionary transitions and more evolutionary stability. Some scientists even propose that impacts played a direct role in the origin of life itself. The energy and pressure of collisions can create complex organic molecules from simpler compounds. Impact sites, with their mix of minerals, heat, and sometimes water, might have provided the perfect laboratories for prebiotic chemistry. There's also the possibility that life itself arrived from elsewhere, carried by meteorites in a process called panspermia. While this remains speculative, if true, the absence of impacts in our solitary universe might mean that the spark of life would need to ignite on Earth alone, without any assistance from beyond. In our actual solar system, Earth is surrounded by a cloud of dust, minute particles from asteroid collisions, and cometary outgassing. Some of this dust spirals inward and eventually enters Earth's atmosphere, where it creates the shooting stars we see on clear nights. In a universe with no asteroids or comets, this cosmic dust would be absent. Our skies would never be streaked by meteors. The zodiacal light, that faint glow sometimes visible after sunset or before dawn caused by sunlight reflecting off interplanetary dust, would never appear. Earth's surroundings would be emptier, cleaner, devoid of even these tiny visitors. This absence would extend to near-Earth objects, the asteroids and comets that periodically pass close to our planet. In our reality, these objects pose a potential impact threat, with the capability to cause regional or even global devastation. In our solitary universe, this threat would not exist. Earth would orbit the Sun in perfect safety, never at risk from cosmic projectiles. However, the absence of near-Earth objects would also remove a potentially valuable resource. Many of these asteroids contain metals, water, and other materials that might someday be harvested for use in space exploration or return to Earth. In a universe where Earth is the only solid body, space resources would be limited to what could be extracted from our own planet. Without the shared history of impacts, Earth would lose one of its connections to the broader universe. Its geological record would tell a story of isolation rather than interaction, of development uninfluenced by external forces. The narrative of our planet would be simpler, but perhaps less rich, missing the chapters written by visitors from space. This isolation extends to our scientific understanding as well. In our actual universe, meteorites provide invaluable information about the early solar system. These cosmic messengers carry within them minerals formed during the birth of the solar nebula, preserving a record of conditions that no longer exist on Earth itself. Scientists study these objects to understand the environment in which Earth formed, the materials available during planetary accretion, and the processes that transformed the solar nebula into the diverse worlds we see today. Without meteorites, this window into the past would be closed. Our knowledge would be limited to what Earth itself preserves, a record that has been extensively reworked by geological processes over billions of years. Comets too serve as scientific time capsules in our universe. These icy bodies preserve materials from the outer solar system, sometimes in their original state from the time of planetary formation. Their compositions tell us about the distribution of elements and compounds in the solar nebula, particularly in the colder regions far from the Sun. In a universe without comets, this scientific resource would be unavailable. Our understanding of the conditions in which Earth formed would be more limited, restricted to what we could infer from Earth itself, rather than observe directly in these pristine cosmic relics. The visual impact of comets would be absent as well. No great comets would grace our skies with their flowing tails. No periodic visitors like Halley's Comet would return on predictable schedules, connecting generations of observers across time. The night sky would be poorer for their absence, limited to the fixed stars and the wandering point of Venus. Even our cultural development might differ in subtle ways, without impacts and their consequences. Many ancient cultures incorporated meteors, shooting stars, and comets into their mythologies. These cosmic visitors were often seen as omens, messages from the gods, or portents of significant events. Without these phenomena, human mythology might have developed along different lines. Modern culture, too, has been influenced by our awareness of cosmic impacts. The realization that extinction-level impacts have occurred in Earth's past and could happen again has entered our collective consciousness, inspiring scientific research, disaster planning, and countless works of fiction. In a world that had never experienced such events, this particular existential concern would never have arisen. There are also implications for Earth's atmosphere and its evolution over time. Impacts, especially large ones, can cause significant atmospheric changes. They inject dust and gases, including carbon dioxide, water vapor, and sulfur compounds. These can trigger short-term climate effects like impact winters, where dust blocks sunlight and cools the planet, as well as longer-term warming from greenhouse gases. Impacts may have also played a role in atmospheric loss and replenishment. Very large collisions can eject atmospheric gases into space, potentially stripping away part of the envelope that surrounds our planet. Conversely, impactors deliver new gases that can help replenish what has been lost. This dynamic of loss and gain has shaped the composition of Earth's atmosphere over billions of years. In a universe where Earth developed in isolation, without these external contributions and disruptions, the atmosphere might have evolved differently. Its composition, density, and structure might all reflect a history of purely internal regulation, rather than a complex interplay between terrestrial and cosmic influences. There's also the question of Earth's volatile elements, those that easily form gases or liquids at relatively low temperatures. Elements like hydrogen, carbon, nitrogen, and the noble gases are relatively rare on Earth compared to their cosmic abundance, because many of them were lost during our planet's hot formation. Some theories suggest that a significant portion of these elements were later delivered by comets and asteroids, particularly those from the outer solar system, where volatile compounds could remain frozen and preserved. Without this delivery system, Earth might be even more depleted in these crucial elements, with potential implications for the development of its atmosphere and eventually life. Carbon in particular is essential for life as we know it. While Earth incorporated some carbon during its formation, impacts may have added significantly to our planet's carbon inventory. A Earth without this cosmic carbon supplement might have less of this crucial element available at its surface, potentially limiting the development of a biosphere. Perhaps most profoundly, the absence of impacts would change Earth's relationship with the rest of the cosmos. In our universe, impacts are a tangible reminder that Earth is not isolated, but part of a larger system. The meteorites we can hold in our hands are pieces of other worlds, direct evidence that matter moves between celestial bodies, connecting them across space and time. This connection has shaped how we understand our place in the universe. The recognition that Earth has been continuously influenced by extraterrestrial material helps us see our planet not as a closed system, but as an open one, exchanging matter and energy with its surroundings throughout its history. In a universe where Earth is the only planet, this connection would be severed. Our world would truly be an island in space, its development shaped entirely by internal forces rather than through dialogue with the broader cosmos. This cosmic isolation might influence how intelligent life, if it emerged, conceived of its relationship with the universe. As we reflect on a world that has never been struck, a planet that developed in pristine isolation without the scars and gifts of cosmic impacts, we gain a deeper appreciation for the complex interplay between Earth and the broader universe in our actual reality. We are not merely on the Earth, but of the Earth, and the Earth itself contains materials that were once part of distant regions of our solar system, delivered here by the asteroids and comets that have helped shape our world. What would Earth become if it had never been struck? Life, the most extraordinary phenomenon we know of in the universe. From microscopic bacteria to towering trees, from darting fish to soaring birds, from crawling insects to running mammals, life in all its diversity and complexity has flourished on our planet for billions of years. But would life still have emerged on an Earth that existed in total cosmic isolation? Would the spark of biology still have ignited on the only planet in the universe? To answer this profound question, we must first consider what life needs to begin. At its most fundamental level, life as we know it requires certain basic ingredients. It needs a medium in which chemical reactions can occur, typically liquid water. It needs energy sources to drive these reactions. It needs a suite of elements and molecules from which to build itself, particularly carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, the so-called CHOMPS elements. And it needs sufficient time and stability for increasingly complex chemical systems to develop. Would our solitary Earth provide these necessities? Let us contemplate each in turn. Water, the universal solvent, the medium in which life began on our actual Earth, would likely still exist on our solitary world, though perhaps in different quantities. While some theories suggest that a significant portion of Earth's water was delivered by comets and water-rich asteroids, others propose that much of our planet's water was incorporated during its formation from the protoplanetary disk. Recent research on the hydrogen isotope composition of Earth's deep mantle suggests that a substantial amount of our planet's water was present from the beginning, trapped within the minerals that accreted to form Earth. If this is correct, then even without later additions from impacts, our solitary Earth might still possess oceans, though perhaps shallower ones. These oceans might have a different chemical composition. In our universe, the seas contain dissolved minerals delivered or influenced by cosmic impacts. The concentration of certain elements, the salinity of the water, the balance of various compounds might all differ in a world untouched by extraterrestrial material. But the essential medium for life, liquid water, would likely still exist. Energy sources would also remain abundant on our solitary Earth. The sun would still shine, providing the light that powers photosynthesis. Geothermal energy would still flow from the planet's hot interior, creating thermal gradients that can drive chemical reactions. Lightning would still flash in storms, delivering intense bursts of energy that can forge complex molecules from simpler ones. The chemical gradients found in environments like deep-sea hydrothermal vents, where hot, mineral-rich water mixes with cold ocean water, would still exist, providing energy sources for potential early metabolic systems. Radioactive decay within Earth's crust and mantle would still release energy that could power certain chemical reactions. In terms of energy, our solitary Earth might be little different from the actual one. The fundamental forces driving potential prebiotic chemistry would remain in place, offering various pathways for complex systems to emerge. But what of the building blocks themselves? Would our solitary Earth have the necessary elements and compounds from which life could construct itself? Here, the absence of cosmic deliveries might have more significant implications. Carbon, the backbone of organic chemistry, was certainly present in the materials that formed Earth, but its availability at the surface might be reduced without the additional contributions from carbonaceous asteroids and comets. Carbon tends to form alloys with iron and can become sequestered in a planet's core during formation. Later impacts helped replenish surface carbon on the actual Earth, a supplement our solitary world would lack. Similarly, nitrogen, crucial for amino acids and nucleic acids, the molecules of life, might be less abundant without deliveries from nitrogen-rich bodies from the outer solar system. Phosphorus, essential for DNA, RNA, and energy transfer molecules like ATP, might also be less available at the surface without the redistributions caused by impacts. The relative abundances of various elements and compounds might differ, creating a different chemical starting point for potential life. The question becomes whether these differences would be prohibitive for life's emergence or merely result in different chemical pathways toward complexity. Even with potentially reduced inventories of certain elements, the fundamental building blocks would still be present to some degree. Carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, and various metals necessary for biological processes would still exist in Earth's crust and oceans. The question is not whether they would be present, but whether their concentrations and distributions would still permit the emergence of complex chemistry. The time for life to emerge would still be available. Our solitary Earth would still form early in the Sun's life, with billions of years of relative stability ahead of it before the Sun's increasing luminosity made the planet too hot for liquid water. Without the disruptions of major impacts, this timeline might even be more favorable for uninterrupted chemical evolution. But time alone is not enough. The right conditions must exist for chemical complexity to increase and eventually cross the threshold into what we would recognize as life. And here, the absence of impacts might have mixed effects. On one hand, without the sterilizing effects of large impacts that may have repeatedly wiped out early life on the actual Earth, nascent biological systems on our solitary world would have more continuous time to develop without interruption. The absence of these reset events might allow for more steady progression toward greater complexity. On the other hand, impacts create unique environments that might facilitate certain steps in prebiotic chemistry. The heat, pressure, and unique mineral assemblages created by impacts can drive chemical reactions that might be crucial for synthesizing some of life's building blocks. The transient but intense conditions created by an impact can produce complex organic compounds that might not form under steady-state conditions. For instance, some research suggests that impacts can create amino acids, the building blocks of proteins, by subjecting simple compounds like carbon dioxide, water, and nitrogen to extreme conditions. Without these natural chemical laboratories, would the path to life be more difficult? Another consideration is the role of hydrothermal systems, environments where hot water circulates through the crust, often as a result of volcanic activity. These systems are considered promising locations for life's origins due to their chemical energy sources, mineral catalysts, and potential for concentrating organic compounds. In our universe, impacts created hydrothermal systems when they struck our planet, adding to those generated by normal geological processes. These impact-generated hydrothermal systems might have provided additional environments for prebiotic chemistry, with unique characteristics based on the composition of the impactor and the target rock. Without these additional settings, our solitary Earth would still have volcanically driven hydrothermal systems, but perhaps a less diverse range of such environments. This might reduce the variety of chemical experiments run by nature in its path toward life, potentially making the emergence of biology less likely, or at least different in character. There's also the question of how the absence of the Moon would affect the potential for life to arise. As we explored earlier, without the Moon, Earth's tides would be much weaker, driven only by the Sun. These diminished tides would create less mixing in coastal waters and fewer intertidal zones where land and sea regularly meet. Some origin of life theories suggest that tidal pools, alternatively wet and dry as tides come and go, provide ideal settings for certain steps in prebiotic chemistry. The wet phase allows molecules to interact in solution, while the dry phase concentrates these compounds and promotes reactions that remove water, such as the formation of peptide bonds between amino acids. Without the Moon's contribution to tides, these cycling environments would be less dynamic, potentially affecting this pathway to life. However, it's important to note that there are many competing theories about where and how life began. While some focus on surface environments like tidal pools or freshwater ponds, others look to deep-sea hydrothermal vents, subsurface environments, or even atmospheric chemistry. Our solitary Earth would still offer many of these alternative settings, even without strong tides or impact-generated environments. The deep oceans, for instance, would still have hydrothermal vents where chemical energy is abundant. Clay minerals, which can catalyze organic reactions and protect fragile molecules, would still form through normal weathering processes. Volcanic activity would still create a variety of environments with diverse chemical conditions. The raw materials and energy sources for life would still exist, even if in different distributions and abundances. There's also the hypothesis of panspermia to consider, the idea that life or its precursors might have been delivered to Earth from elsewhere, perhaps on meteorites. In our universe, certain meteorites contain organic compounds, including amino acids, nucleobases, and other molecules relevant to life. Some theories suggest that these deliveries might have jump-started prebiotic chemistry on Earth, or even delivered already living organisms from another world. In our solitary universe, where Earth is the only planet and no meteorites exist, this potential pathway would be closed. Life would need to emerge entirely from Earth's own resources, without any extraterrestrial supplements or shortcuts. This places more emphasis on indigenous processes and increases the significance of Earth's starting composition. But the fundamental question remains: is life a likely outcome given the right ingredients and conditions? Or is it a cosmic fluke, an extraordinarily rare event that happened on Earth but might easily not have occurred at all? The answer affects how we view the probability of life emerging on our solitary Earth. If life is a natural and likely consequence of chemistry operating under certain conditions, then even with the differences we've described, our solitary Earth might still cross the threshold to biology. The specific chemical pathways might differ, the timing might change, the exact nature of the first living systems might vary, but the fundamental transition from non-life to life could still occur. On the other hand, if life's emergence requires a precise and unlikely sequence of events, a cosmic lottery win rather than an inevitable outcome, then any differences in conditions might significantly affect the probability of that breakthrough moment. The absence of impacts, the lack of a moon, the differences in elemental abundances, all might tip the scales against life's emergence. Current science cannot yet tell us which view is correct. The origin of life remains one of the greatest mysteries in science, with many competing theories, but no definitive answer. We have not yet created life from non-life in the laboratory, though we have synthesized many of life's building blocks and observed some of the chemical steps that might lead toward greater complexity. What we do know is that on the actual Earth, life emerged relatively early in the planet's history. The oldest definitively biological fossils date to about 3.5 billion years ago, and there's suggestive evidence for life as early as 3.8 billion years ago. This means that life appeared within the first billion years of Earth's existence, suggesting that the transition from chemistry to biology can occur relatively quickly given the right conditions. This early emergence might indicate that life isn't extraordinarily unlikely, at least under Earth-like conditions. If life were extremely improbable, we might expect it to have taken much longer to appear, perhaps billions of years more than it actually did. The relatively rapid transition from a young Earth to a living Earth suggests that the path from chemistry to biology might be more accessible than some have thought. If this is true, then despite the differences we've outlined, our solitary Earth might still develop life. It would still have liquid water, energy sources, and at least some inventory of the necessary chemical building blocks. It would still have a variety of environments where prebiotic chemistry could unfold, from the depths of the ocean to the surface of the land. It would still have billions of years for chemical evolution to explore different configurations and pathways. The life that emerged might differ from that on our actual Earth. It might use slightly different biochemical strategies, perhaps incorporating alternative elements or employing different metabolic approaches. It might emerge in a different location or at a different time. But the fundamental phenomenon of self-replicating, evolving systems we would recognize as alive, might still appear. But would this life evolve beyond simple forms? Would it develop the complexity we see in our biosphere, from single cells to vast forests and diverse animals? Here again, we must consider how the absence of other planets, particularly the Moon, and the lack of impacts would affect evolutionary trajectories. Without the Moon stabilizing Earth's axial tilt, our solitary world would experience chaotic changes in its orientation to the Sun over time. As we discussed earlier, this would create wildly varying climate regimes over millions of years, from periods with no seasons to eras of extreme seasonal contrasts. This climatic instability might create substantial challenges for evolving life. Organisms would face intense selective pressure to adapt to these changing conditions. Species unable to cope with the shifting climate regimes might go extinct, while those with greater adaptability would persist. This might favor organisms with shorter generation times, broader environmental tolerances, or specific adaptations for surviving extreme conditions. The overall effect might be a slower progression toward complexity. The constant need to adapt to major environmental changes could consume evolutionary resources that might otherwise be directed toward innovations in body plans, metabolic strategies, or information processing. Life might remain stuck at simpler levels for longer periods, with complex multicellular organisms emerging later, or perhaps not at all. However, it's also possible that the climatic variability might actually accelerate certain aspects of evolution. Changing conditions create new ecological opportunities and drive adaptive radiation. The fluctuating environment might promote genetic diversity and favor organisms with greater phenotypic plasticity, the ability to adjust their development and physiology in response to environmental cues. This could potentially lead to different but equally complex forms of life, adapted to thrive in a more variable world. Instead of the relatively stable ecosystems we see on Earth, life on this solitary planet might develop more fluid ecological relationships, with greater emphasis on adaptability rather than specialization. The absence of major impacts would also affect evolutionary trajectories. In our universe, large impacts have caused mass extinctions, the most famous being the Chicxulub impact that contributed to the extinction of non-avian dinosaurs. These events reset the evolutionary clock, clearing ecological niches and allowing previously marginal groups to radiate into new forms and lifestyles. Without these punctuations, evolution on our solitary Earth might be more continuous, with dominant groups remaining in place for longer periods. The dinosaurs, or their equivalent, might never be removed from their ecological dominance, potentially preventing mammals from diversifying into the forms we see today, including, eventually, humans. This doesn't mean that complex life wouldn't evolve, merely that its history and the specific forms it takes might differ substantially from our familiar terrestrial biology. Intelligence might still emerge, but perhaps in a descendant of a different lineage. Technology might still develop, but created by manipulators very different from human hands. The pace of evolution might also differ. Without the moon's influence on tides, coastal ecosystems would be less dynamic, potentially affecting the transition of life from sea to land. This monumental step in evolutionary history might be delayed or follow a different path in our solitary world. Similarly, the absence of impact-delivered nutrients might affect the productivity of ecosystems. Impacts can redistribute minerals and expose fresh rock, contributing to soil fertility over geological time. Without these occasional supplements, the cycling of nutrients might proceed differently, potentially affecting the capacity of ecosystems to support abundant and diverse life. Yet despite these differences, the fundamental drive of evolution, the process of natural selection acting on heritable variation, would still operate. Life, having emerged, would still adapt to available niches, still develop strategies for obtaining energy and resources, still compete and cooperate in complex ecological relationships. The tree of life might branch differently, but it would still grow. The specific organisms would differ, but ecosystems would still develop, with producers capturing energy, consumers feeding on other organisms, and decomposers recycling nutrients. The details would change, but the patterns might remain recognizable. Intelligence, that remarkable adaptation that allows organisms to model their world internally and act based on these models, might still evolve. It has emerged multiple times in our terrestrial history, in lineages as diverse as cephalopods, corvids, cetaceans, and primates. While human-level technological intelligence appears to be rare, the capacity for complex problem-solving is not, suggesting it offers genuine adaptive advantages in a variety of ecological contexts. Given enough time and relatively stable conditions, similar cognitive abilities might develop on our solitary Earth. The specific organisms possessing this intelligence would likely differ, as would the environments they inhabit and the challenges they face. But the fundamental adaptation of modeling the world to better predict and respond to it might still prove advantageous. Would such intelligent life ever develop technology? Would they build civilizations, discover science, create art? These questions move us beyond biology into the realm of culture, where prediction becomes even more speculative. But there's no obvious reason why intelligence, having evolved, would not eventually apply itself to manipulating the environment in increasingly sophisticated ways. The specific trajectory of technological development would likely differ based on the organisms involved, the resources available, and the environments they inhabit. Tools would be shaped by the manipulators that create them, whether they be hands, tentacles, trunks, or appendages we cannot easily imagine. Materials would be chosen based on local availability and the capabilities of their users to process them. One fascinating difference might arise when these intelligent beings turn their attention to the stars. In our history, astronomy developed early, with humans tracking celestial objects, recognizing patterns, and eventually building mathematical models of their movements. The planets, with their wandering motion against the fixed stars, were objects of particular interest and speculation. But in a universe with only Earth, there would be no other planets to observe. The night sky would show only stars, nebulae, and perhaps galaxies if their instruments grew sophisticated enough. Their astronomy would develop along different lines, focusing on stellar properties and distributions rather than planetary movements and characteristics. This might delay certain insights. In our history, the recognition that the planets orbit the Sun rather than Earth was a crucial step in understanding our place in the cosmos. Without other planets to observe, this realization might come later or through different reasoning. The development of celestial mechanics, gravity, and other fundamental physics might follow alternative pathways. When they eventually developed sufficient technology to look beyond Earth, they would find something profoundly shocking. There are no other worlds. Their planet is not merely rare or special, but unique in the entire universe. The philosophical implications of such a discovery would be enormous, potentially reshaping their understanding of existence in ways we can barely imagine. Would they develop space exploration? With no other planets or moons to visit, the impetus might be reduced, but the urge to leave one's world, to see it from the outside, to experience the void directly rather than through instruments, might still exist. They might still develop spacecraft, still orbit their world, still send probes into the depths of space, even knowing they would find no other solid bodies. One crucial difference would be in their understanding of life itself. In our world, we search for extraterrestrial life, wondering if biology has emerged elsewhere in the cosmos. We study Mars, Venus, and the moons of the gas giants for signs of past or present life. We develop telescopes to examine the atmospheres of exoplanets for biosignatures. We listen for radio signals from technological civilizations. In a universe with only Earth, these searches would be meaningless. The inhabitants of our solitary world would know with certainty that they are alone, that life exists nowhere else, because there is nowhere else for it to exist. Their biology, their evolutionary theory, their conception of life would all develop around this fundamental fact. Life is unique to Earth because Earth itself is unique. This knowledge might foster greater appreciation for the precious nature of their biosphere, or it might lead to greater exploitation, with no concern for preserving archival samples of biological diversity, since there can be no other life elsewhere to compare with their own. The philosophical and ethical implications would be profound, shaping cultural evolution in ways we cannot fully predict. But all of this speculation depends on the initial question: would life emerge at all on our solitary Earth? While we cannot answer with certainty, the evidence suggests that despite the differences we've outlined, the fundamental requirements for life would still be present. Water, energy, carbon, and other essential elements would still exist on Earth's surface. Time and relatively stable conditions would still allow chemical evolution to explore different configurations. The path might be different, the timing might change, the specific biochemistry might vary, but the remarkable transition from non-life to life might still occur. And once begun, the process of evolution would still drive increasing complexity and diversity, though following its own unique trajectory in this solitary world. In the silence of a universe with only one planet, chemistry might still find its way to biology. Molecules might still organize themselves into cells. Cells might still cooperate to form more complex organisms. Life might still emerge and evolve, finding its own path through the possibilities of existence. Life finds a way, but perhaps not the way we know. If life emerged on our solitary Earth, its evolutionary journey would unfold in profound isolation, following rhythms and patterns unlike those of our actual world. With no moon to stabilize Earth's axis, no asteroids or comets to deliver materials or cause extinctions, and no other planets to influence our world even indirectly, evolution would chart a course all its own, guided solely by Earth's internal dynamics and the steady light of the sun. Let us contemplate this alternative history of life, this biological tapestry woven in cosmic solitude. In our actual world, the earliest evidence of life dates back to approximately 3.8 billion years ago, remarkably soon after Earth became habitable. Simple, single-celled organisms dominated the planet for the vast majority of its history, with multicellular life appearing in abundance only about 540 million years ago in the event known as the Cambrian explosion. Would this timeline hold true in our solitary Earth? The early emergence of life might still occur, assuming the necessary ingredients and conditions were present, as we discussed in the previous chapter. But the subsequent evolutionary path would likely diverge significantly from the one we know. Without the moon's stabilizing influence, Earth's axial tilt would vary chaotically over timescales of millions of years. These variations would create wildly different climate regimes. During periods of low axial tilt, the planet would experience minimal seasonal differences, with the equator consistently hot and the poles consistently cold. During periods of high tilt, seasonal extremes would far exceed anything in our world, with dramatic temperature swings between summer and winter, especially at higher latitudes. These shifting climate patterns would create powerful selective pressures on evolving life. Organisms would need to adapt to changing conditions or face extinction. This might favor certain evolutionary innovations over others, potentially altering the course of life's development. One possibility is that the challenging and variable conditions might delay the emergence of complex multicellular life. In our world, the leap from single-celled to multicellular organisms represents one of the major evolutionary transitions, opening new ecological possibilities and eventually leading to the diverse plants and animals we know today. But this transition requires relatively stable conditions over long periods, allowing for the gradual development of cellular cooperation, specialization, and coordination. In a world of fluctuating climate regimes, where the rules change every few million years, the selection pressures might favor organisms that remain adaptable through simpler forms, rather than those that commit to the more complex, but potentially less flexible strategies of multicellularity. Single-celled life might dominate for even longer than it did in our world, with complexity emerging more gradually or taking different forms. When multicellularity did evolve, it might follow different architectural principles. The body plans that emerged during our Cambrian explosion were influenced by the environmental conditions of that time, including Earth's gravity, atmospheric composition, and available ecological niches. With different conditions, different body plans might prove advantageous. For instance, without the moon's gravitational influence creating strong tides, the intertidal zones where land and sea meet would be less dynamic. These regions, which in our world served as important evolutionary laboratories and potential transition zones for life moving from sea to land, would play a reduced role. The colonization of land might follow different pathways or occur later in evolutionary history. The absence of impacts would also profoundly shape evolution's course. In our world, major impacts have caused mass extinctions, events that devastated existing species but created opportunities for survivors to radiate into vacant ecological niches. The most famous of these, the Chicxulub impact that helped end the reign of non-avian dinosaurs, cleared the way for mammals to diversify into forms that eventually included primates and humans. Without these reset events, evolution on our solitary Earth would be more continuous, with dominant groups remaining in power for longer periods. The specific groups that rose to prominence might differ from those in our world due to the altered starting conditions and selective pressures. But once established, they might maintain their ecological dominance for much longer without catastrophic disruptions to clear the biological playing field. This continuity might lead to higher overall biodiversity in some respects, as species would have longer to accumulate and diverge within established ecological frameworks. But it might also lead to less radical innovation, with fewer opportunities for entirely new body plans or adaptive strategies to emerge from the margins and reshape the biosphere. Consider the possibility that the equivalent of dinosaurs in this world, whatever group came to dominate the terrestrial vertebrate niches, might never suffer a catastrophic extinction. Their reign might continue for hundreds of millions of years beyond what occurred in our timeline. The mammals or their equivalents might remain small, nocturnal creatures, never getting the opportunity to diversify into the myriad forms we know, from whales to bats to primates. Intelligence might still evolve, but perhaps in the descendants of these dominant reptilian creatures rather than in the mammalian lineage. This intelligence might have different qualities, emphasizing different cognitive abilities based on the neural architecture available to these organisms. The path to sentience, to creatures that wonder about their place in the universe, would take a different route. But these specific scenarios matter less than the general pattern. Evolution in isolation would follow its own internal logic, shaped by Earth's unique conditions, rather than by external influences. The tree of life would still grow and branch, but in patterns guided by different constraints and opportunities. Even without the dramatic punctuations of mass extinctions, evolution would still experience periods of more rapid change. Internal planetary processes like volcanic eruptions, continental movements, and natural climate fluctuations would still occur, creating new selective pressures and ecological opportunities. Supervolcanic eruptions, for instance, can cause significant cooling by injecting aerosols into the atmosphere, leading to challenging conditions for many organisms. Continental drift gradually creates new geographic arrangements, separating previously connected populations and bringing others into contact, driving speciation through isolation or competition. Sea levels rise and fall with climate changes, alternately connecting and separating landmasses. All these dynamics would still shape evolution on our solitary Earth, creating a complex and changing selective landscape, even without extraterrestrial influences. Life would still need to adapt to changing conditions, still diversify to exploit new opportunities, still compete and cooperate in the endless dance of ecological relationships. One particularly interesting aspect to consider is how the absence of the moon would affect biological rhythms. Many organisms in our world have evolved biological clocks tuned to lunar cycles. Marine creatures time their reproduction to the tides, which are primarily driven by the moon. Some terrestrial species use moonlight to regulate certain behaviors or life cycle events. Without the moon, these lunar adapted rhythms would never evolve. Biological clocks would be tuned solely to daily and annual cycles, with no monthly patterns, and tidal rhythms would be much weaker, driven only by the sun. This might lead to different reproductive strategies, different migration patterns, different activity cycles. The temporal structure of ecosystems would follow different patterns. Similarly, the absence of strong tides might affect the evolution of coastal ecosystems. Intertidal zones in our world are dynamic environments that have driven the evolution of specialized adaptations for dealing with alternating submersion and exposure. Without strong tidal flows, these environments would be less extreme, perhaps leading to less specialized organisms, but also potentially reducing the evolutionary pressure to develop mechanisms for surviving periodic drying. The absence of impacts would remove another source of evolutionary pressure and opportunity. Beyond the major extinction-causing events, smaller impacts have periodically created new environments, introduced new materials to local areas, and otherwise influenced evolution in subtler ways. Without these inputs, the tapestry of evolutionary drivers would be simplified, with terrestrial processes playing an even more dominant role. One consequence of no impacts might be more gradual changes in atmospheric composition over time. Major impacts can release significant quantities of gases, contributing to climate effects. They can also eject atmospheric gases into space during particularly energetic collisions. Without these influences, Earth's atmosphere might evolve more smoothly, potentially affecting the timing and nature of events like the Great Oxygenation, when photosynthetic organisms first flooded the atmosphere with oxygen, dramatically changing conditions for all life. Plate tectonics, the movement of Earth's crustal plates, would still drive mountain building, create and destroy ocean basins, and otherwise reshape the face of the planet over geological time. These processes are internal to Earth and would continue regardless of our planet's cosmic isolation. The specific pattern of continental movements might differ somewhat due to the absence of the moon and major impacts, but the general phenomenon would persist. These tectonic movements would continue to create new biogeographic patterns, separating formerly connected populations and creating opportunities for divergent evolution. The classic example from our world is the separation of South America from other continents, which allowed its mammalian fauna to evolve in isolation, producing unique forms like giant ground sloths and saber-toothed marsupials. Similar natural experiments would unfold on our solitary Earth, driving diversification through geographic isolation and reunion. Climate would still vary over geological time for internal reasons, even without the chaotic axial shifts we've discussed. Changes in greenhouse gas concentrations due to volcanic activity or biological processes, variations in solar output as the sun gradually brightens over its lifetime, and changes in ocean circulation patterns due to continental movements would all drive climate fluctuations on different timescales. These climate shifts would create selective pressures and ecological opportunities, driving evolutionary change. Cooling might favor organisms with better cold tolerance or insulation. Warming might expand the range of tropical adaptations. Drying might drive the evolution of water conservation strategies, while increased rainfall might allow for the expansion of forests and their associated species. Evolution responds to these changes, but it also influences them. The spread of photosynthetic organisms dramatically altered Earth's atmosphere by producing oxygen. The evolution of land plants changed weathering patterns, affecting carbon dioxide levels and thus global temperature. The development of calcifying marine organisms influenced ocean chemistry and the carbon cycle. These feedback loops between life and environment would still operate on our solitary Earth, creating a dynamic ecological theatre in which evolution would play out. The specific actors and scenes might differ from those in our world, but the fundamental processes of adaptation, speciation, competition, and cooperation would continue to drive biological diversification and innovation. Even without external perturbations, extinction would still occur as a natural part of evolution. Species regularly disappear as environments change, competitors emerge, or they simply reach the end of their adaptive potential. New species arise as populations diverge genetically and ecologically. This turnover is a normal feature of evolution, distinct from the mass extinctions that have periodically reset the ecological stage in our world. On our solitary Earth, this background extinction and speciation would continue, but without the dramatic punctuations of impact-induced mass die-offs. The overall pattern might be one of more gradual change, with dominant groups slowly acquiring new adaptations rather than being suddenly replaced by previously marginal lineages. This more continuous evolutionary history might lead to higher overall species richness in some groups, as there would be more time for diversification without major extinction events wiping the slate clean. However, it might also lead to less dramatic innovations, as major shifts in ecological dynamics often follow extinction events that remove established competitors and open new possibilities. The evolution of movement and locomotion might also follow different paths. In our world, the transition from sea to land involved adaptations for supporting body weight against gravity and moving efficiently on solid surfaces. This transition was likely influenced by the nature of the intertidal zones where it occurred, including the tidal patterns driven largely by the moon. With weaker tides, the specific selective pressures during this transition might differ, potentially leading to different locomotor adaptations in terrestrial organisms. The basic challenges of supporting weight and moving on land would remain, but the particular evolutionary solutions might vary based on the specific environments in which the transition occurred. Flight, another major evolutionary innovation, might still evolve, as its advantages in terms of mobility, predator avoidance, and resource access would still apply. But the specific groups that developed flight and the particular mechanisms they employed might differ based on the altered starting conditions and selective landscape of our solitary Earth. Intelligence, that remarkable capacity for complex problem-solving, adaptive learning, and modeling the world internally, has evolved multiple times in our terrestrial history. Cephalopods, corvids, cetaceans, and primates have all independently developed advanced cognitive abilities, suggesting that intelligence offers genuine adaptive advantages in a variety of ecological contexts. Given enough time and relatively stable conditions, similar cognitive capacities might evolve on our solitary Earth. The specific lineages in which they appeared would likely differ, as would the particular neural architectures and cognitive strengths they emphasized. But the fundamental adaptation of modeling the world to better predict and respond to it might still prove advantageous in the complex ecological interactions of any biosphere. If technological intelligence did emerge, its perspective on the cosmos would be profoundly different from our own. In our world, astronomy developed early, with humans tracking celestial objects, recognizing patterns, and eventually building mathematical models of their movements. The planets, with their wandering motion against the fixed stars, were objects of particular interest and speculation. But in a universe with only Earth, there would be no other planets to observe. The night sky would show only stars, nebulae, and perhaps galaxies if their instruments grew sophisticated enough. Their astronomy would develop along different lines, focusing on stellar properties and distributions rather than planetary movements and characteristics. When they eventually developed sufficient technology to look beyond Earth, they would find something profoundly shocking. There are no other worlds. Their planet is not merely rare or special, but unique in the entire universe. The philosophical implications of such a discovery would be enormous, potentially reshaping their understanding of existence and their place in the cosmos. But long before reaching this stage, life on our solitary Earth would have developed in its unique isolation, shaped by internal planetary processes rather than cosmic influences. The specific organisms, ecosystems, and evolutionary patterns would differ from those in our world, but the fundamental processes of life, the underlying chemistry and physics, would remain the same. In this cosmic solitude, where Earth is the only planetary body in existence, life adapts to silence. In this world, evolution is slow and uninterrupted, following its own internal rhythms rather than responding to extraterrestrial punctuations. The tapestry of life weaves itself according to patterns determined by Earth's own processes, creating a biological story unique to this singular world in an otherwise empty universe. In our solitary universe, where Earth is the only planet in existence, would human beings ever come to be? Would creatures resembling us in form and thought emerge from the unique evolutionary pathways of this isolated world? And if something like humanity did arise, how would their civilization, their culture, their understanding of existence differ in a cosmos where their planet truly was the only one of its kind? Let us imagine, for the sake of our contemplation, that despite the different evolutionary history of this solitary Earth, beings similar to humans do eventually emerge. Perhaps not identical to us in their biology or evolutionary lineage, but similar in their essential qualities: bipedal, tool-using, language-capable, socially complex, and possessed of the kind of abstract thinking that allows for art, science, philosophy, and technology. These beings might not be descendants of primates as we are. In a world where the asteroid impact that ended the dinosaurs never occurred, mammals might never have had the opportunity to diversify into forms that could eventually evolve into humans. Instead, perhaps some lineage of dinosaurs or bird descendants gradually developed larger brains, manipulative appendages, and the other attributes that enable technological civilization. Or perhaps, in the absence of that particular impact, a different extinction event driven by internal planetary processes, such as massive volcanism, created similar evolutionary opportunities for a different group. The specific pathway matters less than the possibility that, given enough time and the right selective pressures, something analogous to human intelligence and capability might emerge. How would such beings understand their world and their place in it? How would civilization develop on a planet that truly was alone in the universe, the only solid world orbiting its star or any star? Let us begin with the earliest stages of their cultural development, the equivalent of humanity's prehistoric period. Like early humans, these beings would observe the sky, noting the regular movements of the sun and stars, perhaps developing calendars to track seasonal changes for agricultural or ceremonial purposes. But while our ancestors saw planets wandering among the fixed stars, these beings would see only stars, with no planetary companions moving across the celestial backdrop. This absence might seem minor, but its implications for early astronomy and cosmology could be profound. In our world, the planets were objects of intense interest and speculation from the earliest recorded history. Their movements influenced calendar systems, religious beliefs, and early scientific thought. The word planet itself comes from the Greek for wanderer, highlighting how their motion across the sky distinguished them from the fixed stars. Without these celestial wanderers, the night sky would tell a simpler story. The stars would appear fixed in their positions relative to each other, moving only in their daily and annual cycles across the sky. This might delay certain astronomical insights, making it harder to recognize that celestial bodies move independently through space, rather than being fixed to crystalline spheres, as many ancient astronomers believed. Early religions and mythologies would also develop differently. In our world, many cultures associated planets with deities or powerful spirits, their wandering nature and distinctive appearances inspiring rich mythological traditions. Mars' reddish hue connected it to blood and war in many cultures. Brilliant Venus became associated with love and beauty. Mighty Jupiter took the name of a king among gods. In a world with no planets, these specific mythological connections would never form. The religious systems that developed might focus more exclusively on the sun, moon, stars, and Earth itself. Perhaps the stars would take on even greater mythological significance, with more elaborate stories attached to individual stars or constellations to fill the narrative void left by the absent planets. As these beings developed more sophisticated civilizations, they would begin to ask deeper questions about the nature of their world and the cosmos surrounding it. In our history, the realization that Earth is a planet among planets was a crucial step in understanding our place in the universe. This insight evolved gradually, from early models where Earth stood at the center of all celestial movement to the revolutionary understanding that Earth orbits the Sun among other planets. But in a universe with only Earth, this conceptual path would be blocked. There would be no other planets to observe, no models of planetary motion to develop, no comparative planetology to suggest that Earth itself might be a planet. The uniqueness of Earth in their cosmos would make it categorically different from everything else they could observe, potentially reinforcing geocentric views of the universe for much longer. When these beings eventually developed telescopes and began to study the sky more closely, they would find no companion worlds to observe, no phases of Venus to suggest objects orbiting the Sun, no moons of Jupiter to challenge geocentric models, no rings of Saturn to inspire wonder. The telescope would reveal distant stars, nebulae, and eventually galaxies, but no other world similar to their own. This absence might significantly delay the development of certain scientific insights. In our history, observations of other planets played crucial roles in establishing fundamental physics. Johannes Kepler formulated his laws of planetary motion by analyzing data on planetary positions, particularly Mars. These laws later helped Isaac Newton develop his theory of universal gravitation, a cornerstone of classical physics. Without planets to observe, would these beings develop similar insights? They might still recognize the regular motion of the stars and develop mathematical models to describe these movements. They might still formulate laws of motion by studying objects on Earth. But the bridge between terrestrial and celestial mechanics that planets helped provide in our history would be missing, potentially making the unification of these concepts more difficult. The development of their understanding of gravity might follow a different path. In our world, Newton's realization that the same force that draws an apple to the ground also keeps the moon in orbit around Earth was a crucial insight. This connection between terrestrial and celestial phenomena might be harder to establish without observable planets demonstrating orbital mechanics at different scales. As their science continued to advance, these beings would develop increasingly sophisticated models of the universe, but always with the unique position of Earth as the only world of its kind. When they eventually launched their first space telescopes, they would confirm what ground-based observations had already suggested. Nowhere in the observable universe is there another planetary body. No gas giants, no rocky worlds, no asteroid belts. Just stars, nebulae, black holes, galaxies, and other non-planetary structures. This discovery would represent one of the most profound scientific revelations in their history. Their world is not merely special or rare, but truly unique in the cosmos. This knowledge would likely have far-reaching implications for their philosophy, their science, and their understanding of their own existence. Let us consider how this might shape their development of space exploration. In our world, the desire to visit other planets has been a powerful motivator for space programs. From early lunar missions to Mars rovers to probes visiting the outer planets, much of our space exploration has focused on planetary bodies within our solar system. The search for potentially habitable exoplanets has also driven the development of increasingly powerful telescopes and detection methods. But in a universe with only Earth, what would drive space exploration? With no other planets or moons to visit, the impetus might be reduced. Yet the urge to leave one's world, to see it from the outside, to experience the void directly rather than through instruments might still exist. These beings might still develop spacecraft, still orbit their world, still send probes into the depths of space, even knowing they would find no other solid bodies. Their space program might focus more exclusively on pure science, on studying stars, galaxies, and cosmic phenomena without the emphasis on finding other worlds or potential life that has partly motivated our own space exploration. Their orbital infrastructure might be more extensively developed, with space stations, telescopes, and perhaps eventually habitats, all focused around Earth as the only solid platform in existence. The development of their scientific understanding would follow unique paths in other areas as well. In our world, planetary science provides crucial insights into how worlds form and evolve. Comparing Earth to Venus, Mars, and other bodies helps us understand what makes a planet habitable, how atmospheres develop and change over time, how geological processes operate under different conditions. Without these comparative examples, the beings of our solitary Earth would have only their own world to study. Their geology, atmospheric science, and related fields would be built entirely on Earth observations, without the benefit of seeing how these processes play out on other worlds. This might make certain insights harder to reach, certain theories more difficult to test, certain universal principles more challenging to establish. Their understanding of life and its origins would also develop differently. In our world, the search for extraterrestrial life, both within our solar system and beyond, has significantly influenced our thinking about what life is, how it might begin, and what conditions it requires. The possibility of finding life elsewhere forces us to expand our definitions and consider alternative biochemistries, energy sources, and evolutionary pathways. For beings on a solitary Earth, the uniqueness of their world would mean that life too is unique to their planet. This knowledge might shape their biology in fundamental ways. Without the possibility of alternative life forms elsewhere, they might develop more Earth-centric theories of life's origins and nature. This uniqueness might influence their philosophy and religion as well. In our world, the vastness of the universe and the potential for life elsewhere has challenged many traditional religious views that place humanity at the center of creation. It has inspired both existential anxiety about our cosmic insignificance and spiritual wonder at the grandeur of a universe potentially teeming with life. For beings on a solitary Earth, their unique status as the only planet and the only life in the universe might reinforce certain theological perspectives. They might see their existence as either extraordinarily special, a singular miracle in an otherwise lifeless cosmos, or as profoundly lonely, the sole instance of consciousness in a universe not designed for solid worlds or biological complexity. The psychological impact of this knowledge would likely be significant. How would it feel to know with certainty that you are part of the only life on the only world in the entire universe? That nowhere else in all of existence is there another planet, another ecosystem, another possibility for beings like yourself. This cosmic uniqueness might inspire profound reflection on the meaning and purpose of existence. Some might find this uniqueness exhilarating, a confirmation of their special status in the cosmos. Others might find it isolating, a cosmic loneliness beyond anything we can imagine. These perspectives would likely influence their art, literature, music, and other cultural expressions, creating themes and motifs very different from those in our own culture. The knowledge of their cosmic solitude might also shape their approach to environmental stewardship. In our world, the possibility of finding habitable worlds elsewhere sometimes influences discussions about Earth's environment, with some suggesting that humanity could eventually move elsewhere if Earth becomes uninhabitable, while others emphasize the unlikelihood of finding another world as suitable as our own. For beings on a solitary Earth, there would be absolute certainty that no other habitat exists or could exist. Their world is not merely their only current home, but the only possible home for life in the entire universe. This knowledge might foster a deeper commitment to environmental protection, a recognition that the destruction of their biosphere would be the end, not just of their species, but of all life, everywhere, forever. Or conversely, it might lead to a fatalistic view that since their world is the only one, and since it will eventually become uninhabitable as their star ages, life is ultimately doomed regardless of their actions. This cosmic perspective might influence their thinking about short-term environmental impacts in complex ways. Let us also consider how their understanding of time might differ. In our world, the existence of other planets with different ages and states of evolution gives us a kind of cosmic laboratory for studying planetary development at different stages. We can observe young star systems with protoplanetary disks, mature systems with fully formed planets, and aging systems where planets are affected by their star's evolution. Without this comparative perspective, the beings of our solitary Earth would have only their own world's history to study. They might develop a more linear, less cyclical view of cosmic time. The idea that worlds form, evolve, and eventually end as their stars die would be a theoretical construct rather than an observable reality. Their understanding of deep time might be more Earth-focused, centered on geological and biological evolution, rather than on cosmic cycles of stellar and planetary formation. The development of their technology might also follow different paths. In our world, the space environment has driven the development of numerous technologies, from satellite communications to GPS to remote sensing. The challenges of visiting other planets have pushed advances in propulsion, life support, robotics, and other fields. Without other planets to visit, these specific technological drivers would be absent. Space technology would still develop for orbit and beyond, but the challenges would be different, perhaps more focused on long-duration habitation in space stations, or on deep space exploration with no planetary destinations. The specific problems to solve would differ, and thus the solutions and technologies developed might follow different trajectories. Communication technologies might be particularly affected. In our world, the need to communicate with distant spacecraft visiting other planets has driven advances in deep space communication, including large radio telescopes, precise timing systems, and techniques for transmitting data across vast distances with minimal power. Without planetary exploration missions, these specific technologies might develop more slowly or along different lines. Consider also how their perception of life's fragility might differ. In our world, the existence of other planets provides at least the theoretical possibility that life might exist elsewhere, or that humanity might eventually establish outposts on other worlds, providing a kind of backup for terrestrial life. This influences some of our thinking about existential risks and long-term survival. For beings on a solitary Earth, the knowledge that their world is the only one would mean that the survival of life itself is entirely dependent on the continued habitability of that single planet. There are no backup locations, no other worlds where life might independently exist or where it might be transplanted. This absolute vulnerability might shape their risk assessment and long-term planning in significant ways. Their understanding of probability and the anthropic principle would also take unique forms. In our universe, the existence of many planets raises the question of why life emerged on Earth specifically, leading to discussions of habitable zones, rare Earth hypotheses, and the anthropic principle, which suggests that we observe a universe compatible with our existence precisely because we could only exist in such a universe. In a universe with only one planet, these probabilistic considerations would take a different form. The cosmic coincidence would not be Earth's particular suitability for life among many worlds, but the existence of a planetary body at all in a universe where such structures are unique. This might lead to more teleological thinking, the idea that the universe exists for the purpose of creating their world and their life. Without the comparative examples of many planets with various conditions, it might be harder to recognize the role of chance and selection effects in creating the conditions they observe. Their uniqueness might more readily suggest design or purpose, rather than statistical inevitability within a vast multiverse of possibilities. Let us also consider how these beings might approach the search for extraterrestrial intelligence. In our world, SETI programs scan the skies for signals from technological civilizations, operating on the premise that if life evolved here, it might have evolved elsewhere too. The Drake equation attempts to estimate the number of communicative civilizations in our galaxy based on various factors. For beings on a solitary Earth who know with certainty that theirs is the only planet, these efforts would seem pointless. There can be no other technological civilizations because there are no other worlds for them to evolve on. The silence of the cosmos would not be a puzzle to solve, but a known consequence of their unique status. But might they still listen to the stars? Perhaps, though, with different expectations. Not for signals from other beings like themselves, but perhaps for signs of other forms of intelligence that don't require planets. They might speculate about consciousness arising in stars, in interstellar clouds, in the fabric of space itself. Without the planetary chauvinism that sometimes characterizes our thinking about life, they might be more open to radically different possibilities for mind in the cosmos. Their eventual fate as a civilization would also be shaped by their unique cosmic position. In our world, the possibility of interplanetary expansion provides at least a theoretical path for long-term survival beyond Earth. The vision of becoming a multiplanetary species has inspired much of our space exploration and long-term thinking. For beings on a solitary Earth, this path would be closed. There are no other worlds to colonize, no moons to settle, no Mars equivalent to terraform. Their long-term survival would depend entirely on maintaining their home planet's habitability or on creating entirely artificial habitats in space, drawing resources from their world, or perhaps eventually from stars or interstellar matter. This limitation might focus their long-term planning in different ways. Without the option of planetary expansion, they might invest more heavily in sustainable practices on their homeworld. They might develop more ambitious projects for space habitats, artificial worlds built entirely by their technology, rather than adapted from existing planetary bodies. Their vision might be not of becoming multiplanetary, but of transitioning from natural to artificial habitats, as their star's evolution eventually renders their world uninhabitable. Their approach to time might also differ in fundamental ways. In our world, the existence of other planets, particularly gas giants whose formation and evolution operate on different timescales than Earth, provides a kind of cosmic context for understanding different rates of change and development. We can observe worlds where a year lasts days or centuries, where atmospheric patterns develop over hours or over millennia. Without these comparative examples, the beings of our solitary Earth might develop a more Earth-centric time sense, with the rhythms of their world, its day and year, providing the primary reference frames for understanding time. The idea of other timescales, other cycles, other patterns of duration and succession would be more abstract, without the concrete examples that planets in our system provide. All of these factors would shape the cultural, intellectual, and technological development of these beings in ways quite different from our own history. Yet despite these differences, certain fundamentals might remain similar. The basic drive to understand, to create, to connect, to extend their reach beyond their immediate surroundings might still characterize their civilization as it does our own. They would still gaze at the stars with wonder. They would still seek to comprehend the laws that govern the cosmos. They would still create art that expresses their emotions, their fears, their hopes, their understanding of existence. They would still form communities, develop technologies, explore philosophical questions about meaning, purpose, consciousness, and fate. But always, underlying everything, would be the knowledge of their absolute uniqueness. They, and their world, represent the only instance in the entire universe where matter has gathered into a planetary body, where the complex chemistry of life has emerged, where consciousness has arisen to contemplate its own existence. This knowledge would color everything, from their science to their art, to their religion, to their long-term planning. As they advance technologically, perhaps they would eventually develop theories about why their world is unique. They might formulate explanations involving unusual cosmic constants, rare local conditions during the formation of their star, or even speculative notions about intentional design or purpose. Without comparative examples to study, these theories might remain more speculative than those we can develop in our multiplanetary universe. They might also wonder whether other universes exist beyond their own, universes where planets might be common rather than unique. The concept of a multiverse might hold particular appeal, offering the possibility that while they are alone in their universe, other realities might host countless worlds and myriad forms of life. This cosmic perspective might provide some conceptual relief from the isolation of being the universe's only world. As their civilization matured and their technology advanced, they might eventually face the long-term challenges that all technological species must confront. Their star, like all stars, would gradually change over billions of years, eventually expanding into a red giant that would render their world uninhabitable. With no other planets to migrate to, their options would be more limited than those theoretically available to humanity. They might focus on artificial habitats in space, entirely constructed environments designed to sustain their civilization independent of any planetary body. Or they might develop more exotic technologies aimed at extending their survival, perhaps by modifying their star's evolution or by transforming themselves into forms less dependent on Earth-like conditions. Whatever path they chose, their journey would be shaped by the knowledge that they are the universe's sole planetary inhabitants, the only life that has ever been or will ever be, unless they themselves find ways to create other habitats or seed life elsewhere. This responsibility, this cosmic uniqueness, would influence their decisions, their values, their vision of the future in ways we can only begin to imagine. In contemplating this alternative human story, this narrative of a species that evolves on the only planet in existence, we gain perspective on our own place in the cosmos. We recognize how profoundly our thinking has been shaped by the existence of other worlds, by the knowledge that Earth is one planet among many, that our solar system is one among billions, that the possibility of life elsewhere exists, even if not yet confirmed. Our cosmic context, the fact that we orbit an ordinary star surrounded by other planets in a galaxy filled with other stars and other planets, has influenced our science, our philosophy, our religion, our art, our vision of the future. It has shaped how we understand ourselves and our place in the universe. It has given us both a humbling awareness of our non-special status and an inspiring sense of potential for expansion beyond our world. The beings of our imagined solitary Earth would have none of this context. Their relationship with the cosmos would be defined by their uniqueness, their solitude, their status as the only solid world in an otherwise fluid universe of stars, gas, and energy. This would create a fundamentally different framework for their understanding of existence, their sense of meaning and purpose, their vision of their own future, without other planets to observe. Would we ever look up and wonder? Science as we know it has been profoundly shaped by the presence of other planets. From ancient astronomers tracking the wandering lights across the night sky to modern spacecraft visiting distant worlds, our understanding of the cosmos, of Earth itself, and even of life has developed in dialogue with our planetary neighbors. But in our imagined universe, where Earth stands as the sole planetary body, how would scientific understanding evolve? What insights would come more easily, which would prove more challenging, and which might never emerge at all? Let us explore the development of science on a world without cosmic companions, where researchers have only Earth itself and the distant stars to study. Astronomy, perhaps the oldest science, would develop along dramatically different lines in a universe with only Earth. In our history, the planets were among the first celestial objects to draw sustained scientific attention. Their movements, different from the fixed stars, required explanation and inspired the development of sophisticated mathematical models. In ancient Greece, the attempt to explain planetary motions led to the geocentric model of the universe, with Earth at the center and planets moving in complex combinations of circular paths called epicycles. This model, refined by Ptolemy in the 2nd century, remained dominant in Western thought for over 1,000 years until Copernicus proposed his heliocentric alternative, placing the Sun at the center with Earth and other planets orbiting around it. This revolutionary shift in perspective, from Earth-centered to Sun-centered, represents one of the most significant transformations in scientific thought. But in our solitary universe, there would be no planets to track, no wandering lights whose complex motions demand explanation. The night sky would display only stars, moving together in their daily and yearly cycles across the celestial sphere. Without planets to observe, would the Copernican revolution still occur? Perhaps, but through different reasoning. Astronomers might still eventually recognize that Earth orbits the Sun rather than vice versa, but the evidence would come from observations of stellar parallax, the apparent shift in star positions due to Earth's orbital movement, rather than from attempts to explain planetary motions. This insight might come later in their scientific development, as stellar parallax is subtle and difficult to detect without precise instruments. The heliocentric model might emerge as a theoretical possibility based on mathematical elegance or philosophical considerations, but it would lack the observational support from planetary motions that helped establish it in our history. The absence of planets would affect not just cosmological models, but the very development of observational techniques and instruments. In our world, planets provided highly visible targets for early telescopes. When Galileo first turned his telescope to the night sky in the early 17th century, he observed the phases of Venus, the moons of Jupiter, and the rings of Saturn, all of which provided crucial evidence for the heliocentric model and expanded our understanding of the solar system. Without planets to observe, early telescopes would focus exclusively on stars, nebulae, and eventually galaxies. The phases of Venus, which showed that the planet orbits the Sun, would never be seen. The moons of Jupiter, which demonstrated that not all celestial bodies orbit Earth, would not exist to be discovered. These key pieces of evidence that helped overturn geocentric thinking would be absent. The development of celestial mechanics, the mathematical description of how objects move under gravity, would also follow a different path. In our world, Johannes Kepler's laws of planetary motion, derived from observations of planetary positions, particularly Mars, laid the groundwork for Newton's later universal theory of gravitation. These laws, which describe the elliptical orbits of planets and the relationship between orbital period and distance from the Sun, emerged from the attempt to explain the complex motions of multiple planets. Without planets to study, the specific insights that led to Kepler's laws might never materialize. The mathematical description of orbits might eventually emerge from theoretical considerations or from observations of comets, if they existed in this universe, but the empirical foundation that Kepler built upon would be absent. Isaac Newton's synthesis of terrestrial and celestial physics, unifying the force that makes objects fall on Earth with the force that keeps celestial bodies in their orbits, might still occur, but through a different route. Without multiple planets demonstrating orbital mechanics at different distances from the Sun, the concept of universal gravitation might be harder to establish. Newton might still formulate his laws of motion based on terrestrial experiments, and he might still recognize that the same force that makes apples fall also keeps the Moon in orbit around Earth. But without the comparative examples of multiple planets orbiting at different distances, following predictable mathematical relationships, the extension of these principles to a universal law might be more speculative, less firmly grounded in observation. The field of planetary science, which in our world provides crucial insights into Earth's formation and evolution through comparative studies, would not exist as we know it. There would be no Venus to show the dangers of runaway greenhouse effects, no Mars to demonstrate how a once wet world can lose its atmosphere, no gas giants to reveal how different planetary formation can be under different conditions. Earth science would develop in isolation, without the comparative perspective that other planets provide. Geologists would study Earth's rocks, structures, and processes, without being able to see how these operate under different conditions on other worlds. Atmospheric scientists would analyze Earth's air without the benefit of seeing radically different atmospheres on Venus, Mars, or the gas giants. This isolation might make certain insights harder to reach. In our world, the discovery that Venus has an atmosphere dominated by carbon dioxide, with surface temperatures hot enough to melt lead, helped scientists understand the greenhouse effect and its potential impacts on Earth's climate. Without this extreme example to study, the mechanisms and potential consequences of greenhouse warming might be less clear, identified later, or understood with less certainty. Similarly, observations of Mars have shown us a world that likely had abundant liquid water in its past, but lost most of its atmosphere over time, leading to the arid planet we see today. This history provides valuable perspective on the evolution of terrestrial planets and the factors that contribute to long-term habitability. Without Mars to study, these insights would need to come solely from Earth's geological record, which has been extensively reworked by active geology and might not preserve such clear evidence. The study of Earth's magnetic field, crucial for protecting our atmosphere from solar radiation, has benefited from observations of Mars, which has only a weak localized field, and Mercury, which has a surprisingly strong field for its size. These comparisons help scientists understand how planetary magnetic fields form and evolve. Without these examples, theories of Earth's magnetism would need to be developed without the benefit of seeing how the process plays out under different planetary conditions. Our understanding of plate tectonics, the movement of Earth's crustal plates that drives mountain building, volcanism, and many other geological processes, has been enriched by studying bodies like Mars and Venus, which have different tectonic regimes. These alternative models help explain why plate tectonics operates on Earth and what factors might affect its function. Without these comparatives, the uniqueness and causes of Earth's tectonic system might be harder to identify. Beyond the physical sciences, the absence of other planets would profoundly affect the development of biology, particularly our understanding of life's origins, evolution, and distribution. In our world, the search for life beyond Earth, both within our solar system and on exoplanets, has helped shape our definitions of life, our understanding of habitability, and our theories about how life originates and evolves under different conditions. Without other planets to study or potentially harbor life, biology on our solitary Earth would develop a more Earth-centric perspective. The possibility that life might exist elsewhere, that it might take forms radically different from terrestrial biology, that it might utilize alternative biochemistries or energy sources, would be purely theoretical without the concrete examples of different planetary environments to consider. The field of astrobiology, which examines the potential for life beyond Earth and the conditions that make a planet habitable, would not exist in its current form. Instead, the study of life's origins and evolution would focus exclusively on Earth conditions and Earth life, without the broader context that consideration of other planets provides. This narrower focus might make it harder to recognize which aspects of Earth life are universal, constrained by the fundamental laws of chemistry and physics, and which are contingent, the results of Earth's specific conditions and evolutionary history. Without comparative examples, or at least theoretical models based on other planetary environments, distinguishing the necessary from the contingent in biology would be more challenging. The impact would extend to practical scientific applications as well. In our world, space-based technologies have developed largely in response to the challenges and opportunities of studying and potentially visiting other planets. Communication systems for deep space missions, propulsion technologies for interplanetary travel, and life support systems for potential human exploration have all driven technological innovation. Without other planets to visit or study, these specific technological drivers would be absent. Space technology would still develop for Earth orbit and perhaps for stellar observation. But the particular challenges of planetary exploration would not exist to stimulate certain lines of research and development. Remote sensing technologies, crucial for studying Earth's climate, forests, oceans, and other systems from space, have been refined through their application to other planets. Techniques developed to analyze the atmospheres of Venus and Mars have been adapted to study Earth's air. Methods created to map the surfaces of other worlds have been applied to our own. Without these planetary testbeds, some of these technologies might develop more slowly or along different lines. The absence of other planets would also affect how we study and understand the Sun. In our solar system, the effects of solar radiation, solar wind, and solar magnetic activity can be observed on multiple planets, providing a kind of distributed sensor network for solar phenomena. Without these comparative examples, solar science would rely more exclusively on direct observation and effects detected on Earth alone. Our understanding of time, particularly geological and astronomical timescales, might also develop differently. In our world, other planets provide examples of different rates of evolution and change. Venus may have resurfaced its entire crust in a geologically brief period. Mars shows evidence of dramatic climate shifts over its history. Jupiter's storms persist for centuries, These diverse timescales provide context for understanding Earth's own rhythms of change. Without other planets to observe, the beings of our solitary Earth might develop a more Earth-centric time sense, with the rhythms of their world, its day and year, its geological epochs and evolutionary transitions, providing the primary reference frames for understanding time. The concept of different planetary timescales, of processes that might unfold much faster or slower than on Earth, would be more abstract without concrete examples to study. Perhaps most profoundly, the absence of other planets would affect our understanding of Earth's place in the cosmos. In our world, the recognition that Earth is one planet among many in our solar system, which is one star system among billions in our galaxy, which is one galaxy among billions in the observable universe, has fundamentally shaped our cosmic perspective. It has led to what Carl Sagan called the cosmic perspective, a recognition of both our significance as the only known life in the universe and our insignificance as inhabitants of a typical planet around a typical star. For beings on a solitary Earth, this perspective would be radically different. They would still recognize that their star is one among billions, their galaxy one among many, but they would also know that their world is utterly unique, the only planet in existence. This uniqueness would fundamentally alter how they understand their place in the cosmos, potentially leading to a worldview that simultaneously embraces their cosmic insignificance as inhabitants of one world, among countless stars, and their cosmic significance as the only planet, the only life, the only consciousness in the universe. This dual perspective of uniqueness and smallness might shape their scientific philosophy in ways difficult for us to fully imagine. It might lead to a scientific worldview that places greater emphasis on Earth's special status while still recognizing the vastness and diversity of the cosmic whole. The tension between these viewpoints might drive philosophical and scientific thinking in directions quite different from those in our multifaceted universe. The philosophy of science itself might develop along different lines. In our world, the study of multiple planets has reinforced the principle of mediocrity, the idea that Earth is not special or central, but rather a typical product of common processes. This principle has been a powerful guide in scientific thinking, suggesting that the same physical laws that operate on Earth apply throughout the universe, and that Earth-like conditions are likely not unique. In a universe where Earth is the only planet, this principle would need significant modification. Earth would be demonstrably unique in being the only planetary body, raising questions about why the universal laws that govern star formation, galaxy evolution, and other cosmic processes produced exactly one planet and no more. This uniqueness might challenge the assumption of mediocrity, suggesting instead that Earth represents an extraordinary outcome of otherwise typical processes. Such philosophical considerations might influence the development of theoretical physics, particularly cosmology. In our world, theories about the universe's structure, evolution, and fundamental laws often assume that Earth and our solar system are typical products of common processes. This assumption guides which observations we consider representative and which theories we find plausible. In a universe with only Earth, cosmologists would need to explain why planetary formation happened exactly once. This might lead to very different theories about the early universe, the formation of structure, or even the fundamental constants of nature. The uniqueness of Earth might suggest fine-tuning or unusual conditions, leading to cosmic models quite different from those we develop in our multiplanetary universe. Let us also consider how the absence of other planets would affect the development of specific scientific fields. Planetology would not exist as a comparative discipline, but might develop as a theoretical field, attempting to explain why Earth formed as the universe's only planet. Exobiology would similarly not exist as a search for actual organisms elsewhere, but might develop as a theoretical discipline, exploring why life emerged on the only planetary body. Celestial mechanics would develop not to explain the complex interactions of multiple orbiting bodies, but to account for Earth's solitary orbit around the Sun, and perhaps the behaviors of binary star systems observed in distant space. The rich mathematical frameworks developed to describe multi-body systems in our world would likely be simpler, focused on two-body interactions, rather than the complex resonances and perturbations of multiple planets. In this universe where Earth stands alone, science would still develop, still seek to understand the world through observation, experiment, and theory. But its questions, methods, and perspectives would differ from those in our multiplanetary cosmos. Without comparative examples to study, without other worlds to visit or observe, science would focus more intensely on Earth itself and on the distant stars, seeking to understand both the unique and the universal in a cosmos where Earth represents the only instance of planetary existence. In this universe, science grows but never truly reaches outward. When humans throughout history have looked up at the night sky, they have seen not just stars, but also planets moving among them. These wandering lights, different in their steady glow and their paths across the celestial sphere, have captivated observers for millennia. They have inspired mythology, guided timekeeping, influenced astrology, and eventually led to profound astronomical insights. But in our imagined universe, where Earth is the only planet, the night sky would tell a different story. The visual language of the heavens would be written without some of its most prominent characters. Let us imagine this altered celestial tapestry, this sky with no planets, and contemplate how it would appear to observers on our solitary Earth. The most obvious difference would be the absence of those bright wandering lights. No Venus shining brilliantly as the morning or evening star, sometimes so bright it can be seen even in daylight. No Mars with its distinctive reddish hue, moving with noticeable speed against the background stars during its closest approaches to Earth. No Jupiter with its steady bright glow, outshining all stars except Sirius. No Saturn with its more subdued yellowish light, moving slowly through the constellations over the years. These missing lights would create a simpler, perhaps more uniform night sky. The stars, fixed in their positions relative to each other, would still wheel across the darkness, still group themselves into constellations, still vary in brightness and color. But the dynamic element that planets add to the celestial scene would be absent. The sky would be beautiful, but less complex, missing some of its most noteworthy features. Beyond mere appearance, the absence of planets would change how humans interpret and relate to the night sky. Throughout history, planets have played central roles in many human cultures, influencing religion, mythology, timekeeping, and early science. Their absence would create cultural and intellectual voids that would likely be filled in different ways. In many ancient cultures, planets were associated with deities, their movements tracked and interpreted as divine activities or messages. The Babylonians, Greeks, Romans, Chinese, Maya, and many others developed elaborate mythologies around the planets, often associating them with powerful gods whose characteristics matched the planet's appearance or behavior. Mars, with its red color, became associated with the god of war in many traditions. Brilliant Venus became linked to goddesses of beauty and love. Slow-moving Saturn often represented time and death. Without these wandering lights, mythological systems would develop differently. The specific myths and deities associated with planets would never emerge, requiring different celestial objects or phenomena to serve as divine representatives or omens. Perhaps individual bright stars would take on greater mythological significance. Or maybe transient events like meteors, comets, or novae would play larger cultural roles, despite their temporary nature. Astrological systems, which in our world often give central importance to planetary positions, would either not develop at all or take very different forms. Western astrology, with its emphasis on the planets moving through the zodiac, would certainly not exist in its familiar form. Chinese astrology, which incorporates planetary movements into a complex system of divination, would likewise develop along different lines. Any systems of celestial divination that did emerge would likely focus exclusively on fixed stars, lunar positions, or other available celestial markers. Timekeeping, too, would be affected by the absence of planets. In many ancient cultures, the cycles of Venus, or the positions of Jupiter, helped mark longer time periods beyond the lunar month or solar year. Without planets, calendrical systems might be somewhat simpler, relying solely on the sun, moon, and perhaps the rising and setting of prominent stars to track time. Perhaps most significantly, the development of astronomy itself would follow a different path without planets to observe. As we discussed in the previous chapter, many key astronomical insights came from trying to explain planetary motions. Without these visible puzzles demanding solution, early astronomers would focus on different questions, perhaps giving more attention to stellar properties, the structure of the Milky Way, or the nature of more distant celestial objects. The very act of observing the night sky might feel different in a world without planets. When we look up today, part of what makes the sky dynamic and engaging is the knowledge that it changes night to night, with planets shifting their positions, variable stars changing in brightness, and occasional visitors like comets appearing. Without planets providing easily observable change, the sky might seem more static, its patterns altered only by the predictable daily and seasonal cycles, making it perhaps less inviting to casual observation. For naked eye observers throughout most of human history, the night sky would offer fewer rewards for patient attention. The subtle changes in stellar brightness or color that do occur would be more difficult to detect without instrumentation. The sky would still inspire awe with its vastness and beauty, still serve as a calendar and navigational guide, but it might engage less deeply with the human desire to observe change and pattern. When telescopes were eventually invented, they would reveal a different set of wonders than those first seen by Galileo and his contemporaries. There would be no phases of Venus to observe, no moons of Jupiter to track, no rings of Saturn to puzzle over. Instead, early telescopes would immediately focus on stars, revealing for the first time that many are actually double or multiple systems orbiting each other, and showing that some objects that appear as fuzzy patches to the naked eye are actually clusters of stars or distant nebulae. These stellar discoveries would still revolutionize our understanding of the cosmos, but in different ways. Rather than recognizing Earth's place among the planets, early telescopic astronomers might more quickly grasp the true nature of stars as distant suns, perhaps leading more directly to questions about whether these other suns might have planets of their own, even though none had been observed. The irony, of course, is that in our imagined universe, these other suns do not have planets, because Earth is the only planet in existence. But observers on Earth would have no way of knowing this initially. They might reasonably speculate that other stars could host worlds similar to their own, just as many astronomers in our history did long before we had the technology to detect exoplanets. This speculation would create a poignant situation. A civilization on the only planet in the universe, looking out at the stars and wondering if other planets exist, unaware that theirs is truly unique. The eventual discovery, through advanced telescopes and detection methods, that no other planets orbit any star would come as a profound shock, forcing a radical revision of their understanding of their place in the cosmos. Let us also consider how the appearance of the night sky would be affected by the absence of Venus specifically. As the brightest natural object in the night sky after the moon, Venus can cast visible shadows on Earth and has been observed during daylight throughout human history. Its distinctive cycle as morning and evening star, appearing in the eastern sky before sunrise for about 9 months, then in the western sky after sunset for another 9 months, has made it a particularly important celestial marker for many cultures. Without Venus, the dawn and dusk sky would be noticeably different. No brilliant point of light heralding the sunrise or lingering after sunset. The transition between day and night would feature only the more subtle glow of twilight itself, without this striking stellar beacon. Many mythologies associate Venus with transitions between realms precisely because of its appearance at these liminal times of day. These cultural elements would develop differently or not at all. The absence of Mars would also change the sky's appearance and cultural significance. Though not as bright as Venus, Mars is distinctive for its clearly reddish color, visible even to the naked eye. Without this ruddy wanderer, different myths and associations would emerge, perhaps attaching similar characteristics to red giant stars like Antares or Aldebaran. Jupiter, as the second brightest planet and the most consistently visible throughout the year, would also leave a void in the night sky. Its steady, bright presence has made it an important navigational marker and timekeeper for many cultures. Saturn, while less bright, has a distinctive yellowish appearance to the naked eye and moves so slowly through the zodiac, taking nearly 30 years for a complete circuit, that it has often been associated with time, limitations, and endurance. Without these physical embodiments of time's different scales, from Venus's relatively quick cycle to Saturn's generational journey, human cultures might develop different relationships with temporal cycles. The missing planets represented different rhythms in the sky, different tempos of celestial movement. Their absence would create a sky dominated by just 2 major time frames, the daily rotation of the stars and the monthly cycle of the moon. The cultural impact would extend to art and literature as well. Countless poems, paintings, myths, and stories reference planets, their appearances, and their symbolic meanings. In a world without planets, this artistic vocabulary would be different. The sky would still inspire creative expression, but its portrayal would lack the specific references to planetary characteristics that appear throughout our cultural history. Even language itself would be affected. The days of the week in many languages are named after planets and their associated deities. Sunday and Monday from the sun and moon, Tuesday through Saturday from the 5 visible planets in various linguistic traditions. Without planets, these naming conventions would never develop, requiring different reference for dividing the week, if such a timekeeping unit emerged at all. Beyond cultural considerations, let's contemplate how the physical appearance of the night sky might differ in more subtle ways due to the absence of planets. Without Jupiter's massive gravitational influence, the asteroid belt in our solar system might never have formed in the same way, if it existed at all in this universe where Earth is the only planet. This could mean fewer or different meteor showers, as many of these annual events result from Earth passing through debris trails related to Jupiter's gravitational effects on comets and asteroids. The zodiacal light, that faint, triangular glow sometimes visible along the ecliptic after sunset or before sunrise, might be absent or significantly different. This phenomenon results from sunlight reflecting off dust in the plane of the solar system, much of it produced by asteroid collisions and cometary activity, processes that would be altered in a system with only one planet. Even the apparent structure of the Milky Way as viewed from Earth might appear somewhat different. In our universe, the positions of stars as seen from Earth are influenced in very minute ways by the gravitational effects of the planets, particularly Jupiter. These effects are extremely subtle, but over the long spans of human observation, they contribute to the exact configuration of the night sky we see. A sky with no planetary perturbations would present star positions with subtly different proper motions and distributions. For astronomers in this world, the lack of planets would eliminate certain navigational and calibration references used in our universe. The precisely calculated positions of planets serve as important reference points for aiming telescopes and calibrating instruments. Without these solar system benchmarks, different standards would need to be developed, perhaps relying more heavily on standard stars or other fixed celestial markers. Light pollution, a significant issue in modern times, might develop differently in a world without planets. With no other worlds to potentially visit, space exploration might take a different trajectory, perhaps with less emphasis on rocket technology and more on space telescopes or stations in Earth orbit. This could result in different patterns of satellite deployment and consequently different forms of light and radio interference with astronomical observations. Imagine an observatory on this solitary Earth, its telescopes aimed at the stars. Without planets to study within our solar system, astronomy might more quickly turn its attention outward to the detailed study of stars, nebulae, galaxies, and the large-scale structure of the universe. The objects of study would be more distant on average than those that initially captured attention in our astronomical history, where the planets provided relatively nearby targets for observation and analysis. This outward focus might lead to earlier development of certain astronomical specialties, such as stellar astrophysics or cosmology, at the expense of planetary science, which obviously could not develop as a comparative field. The questions asked, the instruments designed, and the observational programs implemented would all reflect this different emphasis, creating an astronomy more focused on the fundamental nature of stars and the distant universe, rather than on understanding worlds similar to our own. For the general public, interest in the night sky might take different forms. In our world, planets provide accessible targets for amateur astronomers, visible even in small telescopes and showing distinct features like Jupiter's bands or Saturn's rings. These observations often serve as gateways to deeper astronomical interest. Without planets, amateur astronomy might focus more exclusively on stars, star clusters, and nebulae, requiring perhaps a more abstract appreciation of these objects, which generally appear less visually dramatic in small instruments. Public education about astronomy would likewise emphasize different aspects of the cosmos. Instead of the familiar model of the solar system with planets arrayed around the sun, children would learn about stellar types, galactic structure, and cosmic evolution without the intermediate step of understanding planetary systems. The conceptual leap from Earth to distant stars would be more abrupt, without the stepping stones that planets provide in our cosmos. Cultural astronomy, the study of how different human cultures have interpreted and used the night sky, would document very different traditions in this world. The rich mythology associated with planets in our historical record would be replaced by different stories, different celestial characters, different ways of organizing and making sense of the patterns overhead. Constellations might still form the basis of celestial mapping, but the narratives attached to them would not include the journeys of planets through their borders. When space exploration eventually developed, the absence of other planets would create a very different framework for these endeavors. With no Moon, Mars, or Venus to target, space programs would likely focus on Earth orbit, perhaps extending to solar observation or deep space telescopes, but without the concrete goal of visiting other worlds that has driven much of our space exploration history. The philosophical implications of a sky without planets would be profound. In our world, the visibility of other planets has served as a tangible reminder that Earth is one world among many, that our home is a planet itself, part of a family of worlds orbiting the Sun. This understanding has been crucial to developing our cosmic perspective, our sense of Earth as a planet rather than the center of creation. Without visible planets, this perspective might be harder to achieve. The recognition that Earth orbits the Sun rather than vice versa would still eventually emerge through scientific investigation. But the visceral understanding that we live on a planet, a concept reinforced by seeing other planets in the sky, would be less intuitive. Earth might be understood intellectually as orbiting the Sun, but its categorical uniqueness as the only planet might make it harder to fully internalize this perspective. For much of human history, the planets represented a middle realm between the immediate terrestrial environment and the distant, unchanging stars. They were cosmic, but comprehensible, mysterious but observable, distant but part of our solar neighborhood. Their motions helped connect human timescales to cosmic ones. Their varied appearances added diversity to the night sky. Their cycles provided rhythm to celestial observations. Without planets, the night sky would offer a more binary experience, the Earth below and the stars above, without the intermediate category of neighboring worlds. The conceptual space between terrestrial and stellar would be emptier, the cognitive leap from our world to the cosmos larger. The sky would still inspire wonder, still motivate science, still guide navigation and timekeeping, but it would tell a different story, one of greater cosmic isolation. In this universe where Earth stands alone, the night sky would still offer beauty and mystery, still connect us to the larger cosmos, still represent the unknown and the eternal. But it would be a sky that speaks of uniqueness rather than commonality, of isolation rather than community, of exception rather than rule. The stars would still shine, their ancient light still reaching us across the void, but the absent planets would leave a silence in the celestial conversation, a gap in the cosmic narrative that has shaped human culture throughout our history. A night sky that inspires, but never speaks of home. The deepest questions of existence have always been influenced by our understanding of the cosmos. How we perceive our place in the universe shapes how we think about meaning, purpose, consciousness, and value. In our actual world, the knowledge that Earth is one planet among many, orbiting an ordinary star in a vast galaxy that is itself one among billions, has profoundly influenced our philosophical thinking. But in our imagined universe, where Earth is the only planet in existence, how would philosophical thought develop? What unique questions would arise from cosmic solitude? And how would traditional philosophical inquiries transform in response to this singular cosmic context? Let us contemplate the philosophical implications of being truly alone, the only solid world in an otherwise gaseous and energetic universe. At the most fundamental level, the knowledge of Earth's unique status would transform metaphysical thinking, our understanding of the basic nature of reality. In our world, philosophers from ancient times to the present have grappled with questions of necessity versus contingency, asking whether the world as we know it had to be this way or whether it could have been different. The existence of multiple planets, with their various compositions, atmospheres, and characteristics, suggests contingency, the idea that worlds can take many forms based on different initial conditions and evolutionary paths. But in a universe with only Earth, the line between necessity and contingency might blur. Is Earth's existence necessary, ordained by the fundamental laws of physics as the only possible planetary outcome of cosmic evolution? Or is it contingent, a one-in-a-trillion cosmic accident that happened exactly once and never again? Without other planets for comparison, these questions would take on different dimensions, perhaps leading to philosophical perspectives that merge necessity and contingency in unique ways. Philosophers might develop concepts of singular necessity or contingent uniqueness to describe Earth's status, ideas that have no direct parallel in our philosophical tradition because they would emerge from a cosmic context fundamentally different from our own. The fact that planetary formation occurred exactly once in the entire universe would demand explanation, driving metaphysical speculation in directions we can only begin to imagine. Ontology, the branch of metaphysics concerned with the nature of being or existence, would similarly develop along different lines. In our philosophical tradition, questions about what kinds of things exist, how they can be categorized, and what properties define different types of entities have been influenced by the variety we observe in the cosmos. Planets, stars, galaxies, and other celestial objects form natural kinds, categories that help structure our understanding of reality. In a universe with only Earth, the category planet would contain exactly one member. This singularity would raise profound ontological questions. Is a category with only one member truly a category at all? Does Earth represent a universal, a type of thing that could theoretically exist elsewhere but happens not to? Or is it a singularity, a unique entity that defines its own category? These questions would shape how philosophers in this world think about classification, universals, and the structure of reality. The philosophical problem of the one and the many, which explores the relationship between unity and multiplicity, would take on new dimensions. Earth would stand as the only example of planetary unity in a cosmos otherwise characterized by stellar and galactic multiplicity. This contrast might lead to philosophical systems that place special emphasis on the relationship between the unique and the common, the singular and the plural, developing these concepts in ways different from our philosophical traditions. Epistemology, the study of knowledge and how we acquire it, would also be transformed by Earth's solitary status. In our world, comparative planetary science allows us to test theories about how worlds form and evolve, using multiple examples to validate or challenge our models. Knowledge about planetary processes develops through observing various cases and identifying patterns and principles that apply across different worlds. Without this comparative framework, epistemology in our solitary Earth universe would need to rely more heavily on theoretical models, historical reconstruction, and careful observation of Earth alone. The challenge of distinguishing universal principles from Earth-specific contingencies would be greater, potentially leading to more emphasis on thought experiments, counterfactual reasoning, and careful analysis of Earth's internal diversity as a substitute for planetary comparisons. Scientists and philosophers might develop more sophisticated methods for extracting general principles from single instances, recognizing that the usual approach of comparative analysis across multiple examples is unavailable for planetary science. This methodological innovation could influence epistemological thinking more broadly, creating approaches to knowledge that differ from those in our philosophical tradition. The philosophy of science would particularly feel the impact of Earth's uniqueness. In our world, the principle of mediocrity or cosmic average, the idea that Earth is not special, but rather a typical product of common processes, has been a powerful methodological assumption guiding scientific inquiry. This principle suggests that the same physical laws apply throughout the universe, and that Earth-like conditions are likely not unique. In a universe with only Earth, this principle would require fundamental revision. Earth would be demonstrably unique in being the only planetary body, raising questions about why the universal laws that govern star formation, galaxy evolution, and other cosmic processes produced exactly one planet and no more. Scientists and philosophers would need to develop new principles to guide inquiry in a cosmos where Earth represents a genuine exception to the general pattern of non-planetary existence. Perhaps most profoundly, Earth's cosmic solitude would transform existential philosophy, our thinking about meaning, purpose, and significance. In our world, the vastness of the cosmos and the potential for life elsewhere has inspired both existential anxiety about our cosmic insignificance and spiritual wonder at the grandeur of a universe potentially teeming with diverse worlds and beings. For inhabitants of our solitary Earth, existential questions would take different forms. Their world would be simultaneously ordinary, one small planet orbiting one of billions of stars, and extraordinarily special, the only planet in the entire cosmos. This dual status as both cosmically insignificant in size and location, yet absolutely unique in kind, would create a philosophical tension unlike anything in our tradition. Some philosophers might emphasize the profound responsibility that comes with being the only solid world, the only place where consciousness has emerged to contemplate the universe. If Earth is the only planet and Earth life the only life, then the fate of consciousness itself, the universe's awareness of itself, rests entirely on the shoulders of Earth's inhabitants. This perspective might foster a sense of cosmic purpose, a feeling that preserving and extending Earth's biosphere is not merely a local concern, but a matter of universal significance. Others might focus on the apparent cosmic indifference revealed by Earth's singularity. If the universe produced only one planet among trillions of stars, perhaps this suggests that planetary formation, life, and consciousness are cosmic accidents of vanishingly small probability, rather than intended outcomes of natural processes. This view might lead to philosophical positions, emphasizing the ultimate contingency of existence and the need to create meaning in a universe that appears structured to produce stars and galaxies in abundance, but planets only as the rarest of exceptions. The concept of home would take on special philosophical significance. In our world, the idea that other potentially habitable planets might exist offers at least the theoretical possibility of cosmic expansion, of life extending beyond Earth to other worlds. This has influenced philosophical thinking about humanity's future and our relationship with our home planet. For beings on a solitary Earth who know with certainty that no other worlds exist, the relationship with their planetary home would be absolute. There can be no other habitat, no other place where life might take root, no other world to serve as refuge should Earth become uninhabitable. This knowledge might foster a deeper philosophical commitment to Earth as not merely our current home, but the only possible home for any conscious beings, anywhere, ever. This perspective might lead to environmental philosophies more profound than any in our tradition, recognizing that the destruction of Earth's habitability would be not just a local tragedy, but a cosmic one, the end of the universe's only instance of planetary existence and biological complexity. Conversely, it might also inspire fatalistic views, recognizing that as the Sun eventually ages, Earth's habitability will inevitably end, and with it all planetary life in the universe. The tension between these perspectives, between the imperative to preserve the cosmic unique and the recognition of its ultimate impermanence, might drive philosophical innovation, creating new ways of thinking about value, time, and meaning that have no direct parallels in our philosophical tradition. Religious and theological thinking would also develop along different lines in response to Earth's cosmic solitude. In many religious traditions on our Earth, the question of life elsewhere has complicated theological models centered on human uniqueness and special divine concern for humanity. The possibility that other worlds might harbor other beings has forced theological innovation, from pluralistic models that imagine God's relationship with multiple sentient species to anthropocentric views that insist on humanity's uniqueness despite the vastness of the cosmos. In a universe where Earth is demonstrably the only planet, theological thinking would face a different set of challenges. Earth's singular status might more readily suggest design or purpose, the idea that the universe was created specifically to produce this one world and the life it harbors. This might strengthen certain theological perspectives that emphasize Earth's special place in the cosmic order. At the same time, the vast emptiness of space, filled with stars and galaxies, but devoid of other worlds like Earth, might raise profound questions about divine intention. If a creator designed the cosmos, why make it so vast, yet populated with only one planetary world? This apparent disproportion between the vast stage and the singular actor might lead to theological models quite different from those in our traditions, perhaps emphasizing mystery, inscrutability, or cosmic perspectives beyond human comprehension. The philosophy of mind would also be influenced by Earth's uniqueness. In our world, questions about consciousness, its origins, nature, and distribution are shaped by the possibility that mind might have emerged elsewhere in the cosmos. The search for extraterrestrial intelligence represents, in part, a philosophical inquiry into the relationship between consciousness and the physical conditions that support it, asking whether mind is a convergent property that emerges wherever conditions permit or a contingent outcome of Earth's specific evolutionary path. For philosophers on our solitary Earth, these questions would take different forms. Consciousness would be known to exist in exactly one location in the entire universe. This absolute uniqueness might lead to philosophical perspectives that view mind as an extraordinary cosmic exception, perhaps even challenging materialist frameworks that see consciousness as an emergent property of complex systems. If consciousness exists in only one place in the universe, despite the countless stars and galaxies, might this suggest something exceptional about Earth, life, or mind itself? This question could drive philosophical speculation about the relationship between consciousness and the physical world, potentially leading to perspectives that see mind as more fundamental to reality than typical in our materialist scientific tradition. Ethical philosophy would likewise develop in dialogue with the knowledge of Earth's cosmic uniqueness. In our world, environmental ethics often appeals to the rarity or even uniqueness of Earth as a habitable world, arguing for the preservation of biospheric integrity on the grounds that Earth is, as far as we know, the only home available to us. For inhabitants of a demonstrably solitary Earth, this ethical framework would be absolute rather than provisional. They would know with certainty that their world is not merely rare, but genuinely unique, the only planet in the entire universe. This knowledge might foster a deeper sense of ethical responsibility toward the biosphere, recognizing that the destruction of Earth's habitability would be the end not just of human existence, but of all planetary life in the universe, with no possibility of continuation elsewhere. This perspective might lead to ethical philosophies that place absolute value on the preservation of Earth's biospheric integrity, viewing it not merely as instrumental to human flourishing, but as intrinsically valuable as the universe's only instance of planetary existence and biological complexity. The specific ethical frameworks that would emerge from this cosmic context might differ substantially from those in our philosophical tradition. Political philosophy, too, would be influenced by the knowledge of Earth's cosmic solitude. In our world, the recognition that Earth is one planet among many has sometimes been invoked to encourage global cooperation, suggesting that our common planetary identity transcends national or cultural divisions. The overview effect experienced by astronauts who report a cognitive shift upon seeing Earth from space as a unified whole without visible borders has inspired philosophical perspectives, emphasizing planetary citizenship. For inhabitants of a solitary Earth, this unified perspective might be even more pronounced. The knowledge that their world is the only planet in existence might foster stronger recognition of humanity's common fate and shared responsibility as stewards of the universe's only planetary biosphere. This might encourage political philosophies that place greater emphasis on global governance, intergenerational ethics, and the long-term preservation of Earth's habitability. Conversely, the recognition of Earth's ultimate cosmic insignificance in terms of size and location, despite its uniqueness as a planetary body, might reinforce philosophical perspectives that view large-scale political projects with skepticism. If planetary existence is a cosmic accident of vanishingly small probability, perhaps this suggests embracing the local and immediate rather than pursuing grand visions of the future. The tension between these perspectives, between cosmic responsibility and cosmic insignificance, might drive innovation in political philosophy, creating new ways of thinking about governance, citizenship, and collective action that respond to the unique cosmic context of a solitary Earth. Aesthetics, the philosophical study of beauty and artistic expression, would also develop in dialogue with the knowledge of Earth's cosmic uniqueness. In our world, artistic imagination often extends to other worlds, envisioning landscapes, creatures, and civilizations beyond Earth. Science fiction, in particular, has explored the aesthetic and philosophical implications of cosmic plurality, imagining diverse worlds and beings that throw our own existence into new perspective. For artists and philosophers on our solitary Earth, aesthetic expression would be confined to the actual and the abstract, without the halfway house of imagined other worlds. Artistic imagination might focus more intensely on Earth itself, exploring its diversity and complexity with greater attention, or turn toward more abstract realms disconnected from planetary existence. The specific aesthetic traditions that would emerge in this context might differ significantly from those in our artistic history. The concept of the sublime, which explores our aesthetic and emotional response to phenomena that overwhelm the senses or imagination, might take on special significance. The knowledge that Earth is the only planet in a cosmos of unimaginable vastness might create a unique form of the cosmic sublime, a response to the tension between Earth's absolute uniqueness and its tiny place in the grand scheme of things. The philosophy of language would also feel the impact of Earth's cosmic solitude. In our world, the concept planet refers to a class of objects with multiple members. We understand what a planet is partly through observing the similarities and differences between Earth, Mars, Venus, Jupiter, and others. The meaning of the term emerges from this comparative context. In a universe with only Earth, the term planet would refer to a class with exactly one member. This singularity would raise interesting questions about reference, meaning, and category formation. Can we truly understand what a planet is if we have only one example? Would the concept be more like a proper noun referring to a unique entity? Or would it still function as a category term, describing a type of thing that happens to have only one instance? These linguistic considerations might lead to philosophical innovations in how we think about reference, meaning, and the relationship between language and reality. The specific theories that would emerge might differ from those in our philosophical tradition, which developed in a context where most natural kind terms refer to categories with multiple members. Time philosophy would also be influenced by Earth's cosmic solitude. In our world, the existence of other planets, particularly the gas giants with their different rates of formation and evolution, provides a kind of cosmic context for understanding different timescales. We can observe worlds where a year lasts days or centuries, where atmospheric patterns develop over hours or over millennia. Without these comparative examples, philosophers on our solitary Earth might develop a more Earth-centric time sense, with the rhythms of their world, its day and year, its geological epochs and evolutionary transitions, providing the primary reference frames for understanding temporal flow and scale. The specific philosophical questions about time's nature, passage, and measurement might take different forms in this context. The very concept of possibility would be transformed by Earth's uniqueness. In modal philosophy, which explores necessity, possibility, and contingency, the existence of multiple planets with different characteristics suggests a space of planetary possibility, a range of ways worlds can be. This informs how we think about counterfactuals, alternative possibilities, and the relationship between the actual and the possible. In a universe with only Earth, the space of planetary possibility would be purely theoretical, with no actual examples beyond our world. This might lead to different approaches to modal thinking, perhaps placing greater emphasis on logical or conceptual possibility rather than on physically instantiated alternatives. The specific modal philosophies that would emerge might differ from those in our tradition, which developed in a context where physical variation provides concrete examples of alternative possibilities. Let us also consider how Earth's cosmic solitude might influence phenomenology, the philosophical study of conscious experience. In our world, the knowledge that Earth is one planet among many shapes how we experience our place in the cosmos. The pale blue dot perspective, seeing Earth as a tiny point of light in the vastness of space, influences our subjective sense of cosmic scale and significance. For beings on our solitary Earth, the phenomenology of cosmic awareness would be different. They would know that their world, while small in the cosmic scale, is also absolutely unique, the only planet in existence. This dual awareness of insignificance and uniqueness might create a phenomenological tension unlike anything in our experience, potentially leading to new ways of articulating the felt quality of cosmic awareness. As philosophical traditions developed on this solitary Earth, they would continually return to the central fact of their world's cosmic uniqueness. exploring its implications from different perspectives and through different conceptual frameworks. Some traditions might emphasize the responsibility that comes with being the universe's only planetary inhabitants, developing ethical and political philosophies centered on preserving this cosmic singularity. Others might focus on the apparent indifference of the cosmos, the vast emptiness that surrounds Earth's solitary existence, developing existential perspectives that emphasize the creation of meaning in a universe that produced exactly one planet among countless stars. The dialogue between these perspectives, between cosmic significance and cosmic indifference, between uniqueness and isolation, would drive philosophical innovation, creating traditions of thought that reflect the unique cosmic context of a universe with only one planet. Through this philosophical exploration, the inhabitants of our solitary Earth would seek to understand not just what it means to exist, but what it means to be truly alone, the only solid world in a universe otherwise composed of stars, gas, and empty space. Loneliness can be peaceful, but it also asks why. Astronomy, the oldest of sciences, has always been driven by discovery. From ancient stargazers noting the wandering lights of planets to modern telescopes revealing distant galaxies, the history of astronomy is a story of expanding horizons, of finding new objects and phenomena that challenge our understanding and broaden our cosmic perspective. But in our imagined universe, where Earth is the only planet, astronomy would develop along profoundly different lines. Without planets to discover, without moons or asteroids or comets to observe, how would the study of the heavens unfold? What would drive astronomical inquiry, and what insights would emerge in this more limited cosmic context? Let us explore astronomy without the discovery of other worlds, a science focused solely on stars, nebulae, galaxies, and the broader cosmic structures they form. The earliest astronomy on our solitary Earth would likely develop much as it did in our history, with naked eye observations of the stars, tracking their positions, motions, and occasional variations in brightness. Early astronomers would note the fixed patterns of stars we call constellations, the band of light across the sky we know as the Milky Way, and perhaps occasional transient phenomena like novae, supernovae, or comets, if these latter objects existed in this universe. Without planets to track, early astronomical efforts would focus exclusively on these fixed and transient stellar phenomena. Star catalogues would be compiled, recording positions, apparent brightnesses, and colors. The regular cycles of the celestial sphere, driven by Earth's rotation and orbit around the Sun, would be recognized and used for timekeeping and navigation. The zodiac might still be defined as the band of constellations through which the Sun appears to move throughout the year, but it would lack the additional significance it gained in our world from the planets also moving through this celestial zone. Mathematical astronomy would still develop to predict the positions of celestial bodies, but without the complex planetary motions to account for, these models might be simpler, focused solely on the regular paths of the Sun and stars across the sky. The mathematical challenge of describing retrograde planetary motion, which in our history led to the complex epicycle models of Ptolemy, and eventually to the heliocentric revolution of Copernicus, would never arise to drive astronomical theory in these particular directions. The development of the heliocentric model might still occur, but through different reasoning. Without planetary motions to explain, the initial impetus for placing the Sun at the center of the system would be reduced. The geocentric perspective, with Earth at the center of the celestial sphere, might persist longer as a natural description of appearances. The eventual recognition that Earth orbits the Sun, rather than vice versa, would need to come from other evidence, such as the detection of stellar parallax, the apparent shift in star positions due to Earth's orbital movement, or from theoretical considerations about the relative masses of Earth and the Sun once these could be estimated. The invention of the telescope would still revolutionize astronomy, but with different initial discoveries. In our history, when Galileo first turned his telescope to the night sky in 1609, he observed the phases of Venus, the moons of Jupiter, and the rings of Saturn, all of which provided crucial evidence for the heliocentric model and expanded our understanding of the solar system. He also observed the moon's craters and mountains, revealing it as a world with Earth-like features rather than a perfect celestial sphere. In our solitary Earth universe, early telescopes would immediately focus on stars and nebulae rather than planets or moons. The first telescopic discoveries might include the resolution of the Milky Way into countless individual stars, the observation that many stars are actually double or multiple systems orbiting each other, and the identification of various types of nebulae, from star clusters to gaseous clouds to what we now know as galaxies. These discoveries would still revolutionize our understanding of the cosmos, but in different ways. Rather than recognizing Earth's place among the planets, early telescopic astronomers might more quickly grasp the true nature of stars as distant suns and the vast scale of the universe beyond our local neighborhood. The conceptual shift might be more immediately from an Earth-centered perspective to a cosmic one, without the intermediate step of understanding the solar system as a family of worlds. The development of spectroscopy in the 19th century would still transform astronomy, revealing the chemical composition of stars through analysis of their light. This would still lead to the classification of stars into different types based on their spectra, temperature, and other properties. The recognition that stars are not all identical, but vary in size, temperature, composition, and evolutionary state would still emerge, providing insights into stellar life cycles and the production of elements through nuclear fusion. Without planets to study, astronomers might focus more intensely on stellar properties and behavior from an earlier stage. The classification of variable stars, which change in brightness over time, might receive more attention, as would stellar structure and evolution. The HR diagram, which plots stars by their temperature and luminosity, revealing patterns that reflect different stellar types and life stages, might emerge earlier as a central organizing principle in astronomical research. The study of binary and multiple star systems would likely be a major focus. In our universe, about half of all stars exist in binary or multiple systems, orbiting around their common center of mass. These systems provide valuable natural laboratories for studying stellar masses, evolutionary paths, and gravitational interactions. Without planets to observe, astronomers on our solitary Earth might place even greater emphasis on these stellar partnerships, using them to test theories of gravitation and stellar evolution. The discovery of interstellar medium, the gas and dust between stars, would still occur, leading to insights about the birth of new stars from collapsing clouds of material. Star-forming regions like the Orion Nebula would still be observed and studied, revealing the processes by which stars come into being. The question of why these same processes formed exactly one planet in the entire universe would become a profound scientific mystery, driving theoretical work on the unique conditions that might have led to Earth's formation. The recognition of our galaxy, the Milky Way, as a vast island of stars would still emerge, along with the eventual discovery that many of the nebulae observed in telescopes are actually distant galaxies, island universes in their own right. The expansion of the universe, revealed by the redshift of distant galaxies, would still be discovered, leading to the development of modern cosmology, with its theories of the Big Bang, cosmic inflation, and the evolution of large-scale structure. These fundamental discoveries about the broader cosmos would still occur, but always with the puzzling absence of other planets. As astronomical knowledge advanced and telescopes grew more powerful, revealing billions of stars in our galaxy and billions of galaxies beyond, the uniqueness of Earth as the only planet would become increasingly striking. The fact that not a single other star hosts planets, despite the countless opportunities for planetary formation, would demand explanation. This absence might drive the development of theoretical models suggesting that planetary formation requires extraordinarily rare conditions that occurred exactly once in cosmic history. Or it might lead to theories proposing that planets once were more common, but were systematically removed by some unknown process, leaving only Earth as a survivor. The specific models would likely differ significantly from those in our astronomy, which must explain the observed abundance of planets, rather than their cosmic rarity. The search for planets around other stars, which has been a major focus of astronomy in recent decades, would obviously not develop in the same way on our solitary Earth. Astronomers might still develop the technical capabilities to detect planets through methods like radial velocity measurements or transit photometry, but they would find none to detect. Each star examined would show no sign of orbiting planets, reinforcing the unique status of Earth in the cosmos. this consistent negative result would itself become a subject of intense scientific interest. Why do no other stars host planets? What makes our Sun unique in having produced exactly one planet? Is there something fundamentally different about our star, or did some incredibly rare confluence of events occur here and nowhere else? These questions would drive both observational astronomy, looking for subtle differences between our Sun and other stars, and theoretical work, modeling the specific conditions that might allow planetary formation in just one case across the entire universe. The field of astrobiology, which in our world explores the potential for life beyond Earth, would take a very different form. Without other planets to study, the focus would be more theoretical, asking why life emerged on the only planetary body in existence and whether it could potentially exist in non-planetary environments, such as within stars, interstellar clouds, or other exotic settings. The recognition that Earth hosts the only life in the universe would be based not on lack of evidence despite searching, as in our world, but on the fundamental absence of other potentially life-supporting environments. Space-based astronomy would still develop, with telescopes placed in orbit to avoid the distorting effects of Earth's atmosphere and to observe wavelengths that don't penetrate to the surface. But the specific questions driving these missions would differ. Without planets to study within our solar system, without exoplanets to search for around other stars, space telescopes would focus exclusively on stellar, galactic, and cosmological observations. The Hubble Space Telescope, which in our world has studied everything from planets in our solar system to distant galaxies, might have an analogue dedicated purely to deep space observation. The James Webb Space Telescope, designed in part to study exoplanet atmospheres, would have no such targets in a universe with only Earth, and so might be designed exclusively for observing the early universe, distant galaxies, and star formation. Without planetary science to drive certain technological developments, astronomical instrumentation might evolve along different paths. The specific challenges of detecting faint planets near bright stars, of resolving planetary disks, of analyzing planetary atmospheres, would never arise to stimulate these areas of technical innovation. Instead, instrument development might focus more intensively on stellar and galactic observation, perhaps advancing more rapidly in these specific areas due to the concentrated effort. The field of radio astronomy, which studies celestial objects through their radio frequency emissions, would still develop, revealing phenomena like pulsars, quasars, and the cosmic microwave background radiation. These discoveries would still revolutionize our understanding of neutron stars, active galactic nuclei, and the early universe. But the search for radio signals from potential extraterrestrial civilizations, which has been a small but persistent aspect of radio astronomy in our world, would never emerge as a scientific pursuit, given the known absence of other planets where such civilizations could arise. The study of cosmic rays, high-energy particles originating from beyond Earth, would still develop, revealing information about energetic processes in distant objects like supernovae, neutron stars, and active galactic nuclei. Neutrino astronomy, which detects these elusive particles to study stellar cores and other energetic phenomena, would still emerge as technology advanced. Gravitational wave astronomy, which in our world recently opened a new window on the cosmos by detecting ripples in space-time from merging black holes and neutron stars, would still develop along similar lines. These fields of study beyond traditional optical astronomy would still expand our understanding of the cosmos, revealing invisible aspects of celestial objects and events. The specific questions asked and phenomena studied might differ somewhat from those in our astronomy, but the general progression toward a more complete picture of the universe through multiple observational channels would likely follow similar patterns. The absence of planetary science might actually accelerate progress in some areas of astronomy by focusing attention and resources more exclusively on stellar, galactic, and cosmological questions. Without the technical challenges and scientific questions associated with planetary observation, astronomers might advance more rapidly in understanding certain aspects of stars, interstellar medium, galaxies, and large-scale cosmic structure. For instance, stellar seismology, which studies oscillations in stars to understand their internal structure, might receive greater emphasis earlier in the development of astronomy. The detailed mapping of our galaxy's structure, including its spiral arms, central bar, and surrounding halo, might advance more quickly. The properties of dark matter and dark energy, which together make up about 95% of the cosmos, might be investigated more intensively from an earlier stage. These potential advances in specific areas would be balanced against the loss of insights that, in our world, came from comparative planetary studies. The understanding of atmospheric physics, geophysics, and many other fields has been enriched by observing how these processes operate under different conditions on various planets. Without these comparative examples, certain insights about Earth itself might be harder to achieve, even as progress in purely stellar and galactic astronomy might accelerate. The cultural impact of astronomy would also differ in a universe with only Earth. In our world, the discovery of other planets, both in our solar system and beyond, has captured public imagination and inspired both scientific interest and creative expression. The potential for life elsewhere, the possibility of visiting or even colonizing other worlds, the wonder of seeing landscapes no human has ever observed before, all have helped drive public support for astronomy and space science. In a universe with only Earth, astronomy might be more abstract from a public perspective, focused on distant stars and galaxies rather than on potentially familiar worlds. The inspirational value of discovering new planets, of imagining standing on the surface of Mars or floating in the clouds of Venus, would be absent. Astronomy would need to draw support and inspiration from other sources, perhaps focusing more on the fundamental nature of the cosmos, the life cycle of stars, or the evolution of galaxies. The philosophical implications of astronomical discoveries would also differ. In our world, finding numerous planets around other stars has reinforced the principle of mediocrity, the idea that Earth is not special, but rather a typical product of common processes. This has influenced how we think about our place in the cosmos and the likelihood of life elsewhere. In a universe where Earth is demonstrably the only planet, astronomical discoveries would consistently reinforce Earth's exceptional status. Each star examined and found to host no planets would strengthen the understanding that our world represents a cosmic anomaly, the only instance where matter gathered into a planetary body. This uniqueness would shape philosophical reflections on our place in the universe, potentially leading to perspectives that see Earth as either extraordinarily special or utterly accidental, depending on the theoretical framework adopted to explain its singular existence. The practice of amateur astronomy would also differ in a universe with only Earth. In our world, planets provide accessible and visually impressive targets for amateur observers. Jupiter's bands and moons, Saturn's magnificent rings, Mars' polar caps, and Venus's phases can all be observed with relatively modest equipment, providing rewarding experiences that often serve as gateways to deeper astronomical interest. Without planets to observe, amateur astronomy might focus more exclusively on stars, star clusters, nebulae, and galaxies. While many of these objects are visually stunning, they generally require darker skies and sometimes more advanced equipment to observe well, potentially making astronomy less immediately accessible to beginners. The specific culture and practices of amateur astronomy that would develop in this context might differ from those in our astronomical community. Scientific education about astronomy would likewise emphasize different aspects of the cosmos. Instead of the familiar model of the solar system with planets arrayed around the sun, children would learn about stellar types, galactic structure, and cosmic evolution without the intermediate step of understanding planetary systems. The conceptual leap from Earth to distant stars would be more abrupt, without the stepping stones that planets provide in our cosmos. As astronomical knowledge advanced, the mystery of Earth's unique status would likely become more rather than less profound. In our universe, as we've discovered thousands of exoplanets, we've found that planetary formation appears to be a natural outcome of star formation, with most stars hosting planetary systems of some kind. This makes our solar system seem less special, more a typical product of common processes. But in our solitary Earth universe, the opposite would occur. As more stars were studied and found to host no planets, as our understanding of stellar formation and evolution advanced without revealing other planetary systems, Earth's status as the sole planet would become increasingly puzzling. The more we learned about the cosmos, the more striking and demanding of explanation Earth's uniqueness would become. This might drive astronomical theory in unique directions, perhaps toward concepts like multiverse models, where our universe with exactly one planet represents one possibility among many different universes, with varying conditions and outcomes. Or it might lead to anthropic reasoning, suggesting that we observe a universe with exactly one planet because that one planet is necessary for our existence as observers. The specific theoretical frameworks developed to address Earth's cosmic solitude might differ significantly from those in our astronomy. The ultimate fate of astronomy on our solitary Earth might be both more focused and more limited than in our universe. More focused, in that the absence of planetary science would concentrate attention on stellar, galactic, and cosmological questions. More limited, in that the lack of comparative planetary examples would restrict certain avenues of inquiry and leave some questions about Earth itself harder to answer. As technology advanced, astronomers would develop increasingly powerful tools for studying the distant universe, from space telescopes observing across the electromagnetic spectrum to detectors for cosmic rays, neutrinos, and gravitational waves. These instruments would reveal the cosmos in ever greater detail, from the earliest moments after the Big Bang to the most energetic events in distant galaxies. But always, underlying this expanding knowledge of the broader universe would be the persistent mystery of Earth's unique status. Why, in a cosmos with billions of galaxies, each containing billions of stars, is there exactly one planet? What confluence of conditions or processes led to Earth's formation, while preventing the formation of planets anywhere else? How did the only solid world in the universe come to host the only life, the only consciousness, the only beings capable of asking these questions? These inquiries would drive astronomical research, theoretical modeling, and philosophical reflection in this solitary Earth universe. They would shape the development of the science, the questions it asks, the instruments it builds, and the theories it proposes. Astronomy would still advance, still reveal new wonders and insights about the cosmos, but always in dialogue with the fundamental mystery of Earth's cosmic isolation. In this universe of one planet, astronomy would still look up, still seek to understand the stars and galaxies beyond our world. It would still accumulate knowledge, still develop theories, still build instruments to peer deeper into space and time. But it would do so knowing that Earth stands utterly alone as a planetary body, the only instance in the entire cosmos where matter gathered into a solid world orbiting a star. This knowledge would color everything, from the specific questions asked to the theories proposed to the philosophical implications drawn from astronomical discoveries. Astronomy without the discovery of other worlds would still be a rich and rewarding science, but one shaped by the profound awareness of Earth's unique status in a universe otherwise filled with stars, gas, and empty space. We would still look up, but what would we find? Only echoes. Throughout our exploration of a universe where Earth stands as the only planet, we have contemplated the implications of cosmic solitude, the unique development of a world without planetary neighbors. But need this solitude be permanent? Might the universe, in its vast expanse of space and time, eventually produce other planets long after Earth's formation? Could our solitary world one day find itself with unexpected cosmic companions, challenging the assumption of eternal planetary uniqueness? Let us consider these possibilities, examining the potential pathways by which new planets might emerge in a cosmos that initially created only one. In our actual universe, most planets form early in a star's life, condensing from the protoplanetary disk of gas and dust that surrounds young stars. This process typically occurs within the first few million years of a star's existence, before the remaining disk material is blown away by stellar winds or radiation. But this is not the only conceivable pathway to planetary formation. One alternative mechanism involves the rare but possible formation of planets around dying stars. As stars like our Sun exhaust their nuclear fuel, they expand into red giants before eventually shedding their outer layers, creating spectacular planetary nebulae while leaving behind dense stellar cores called white dwarfs. This process disperses enriched material into space, material that might, under certain circumstances, form new disks around the stellar remnant. In a universe where planets are extraordinarily rare, perhaps forming only once in the entire history of the cosmos, could these unusual second-generation disks provide another opportunity for planetary birth? Might the enriched material ejected by dying stars containing higher proportions of heavy elements formed through stellar nucleosynthesis, create conditions more favorable for planetary formation than those that prevailed earlier in cosmic history? If so, then as stars in our solitary Earth universe age and die, some might develop these second-chance disks, potentially giving rise to new planets billions of years after Earth's formation. These would not be planets in the traditional sense of worlds orbiting main-sequence stars, but rather bodies circling the dense remnants of stellar death, white dwarfs or neutron stars. Such planets would be very different from Earth, orbiting dim, cooling stellar cores rather than bright, energetic stars. They would receive little light or heat. Their surfaces, if solid, would likely be frozen to extreme depths. Any atmospheres would be perpetually frigid, with temperatures approaching absolute zero. These would be dark worlds, illuminated only by the faint glow of their dying stars and the distant pinpricks of other stars and galaxies. Yet they would be planets nonetheless, solid bodies orbiting stellar objects, breaking Earth's cosmic monopoly on planetary existence. Their detection, perhaps billions of years in the future, would transform the universe from one with a single planet to one with at least a few, challenging the assumption of Earth's absolute uniqueness that had prevailed for so long. Another possibility involves the very rare but not impossible formation of planets through direct gravitational collapse, without the need for a protoplanetary disk. In our universe, giant planets might occasionally form through a process similar to star formation, where a region of a molecular cloud becomes dense enough to collapse directly under its own gravity. These planets would not orbit stars, but would instead wander the interstellar void as rogue or free-floating planets. In our solitary Earth universe, where planetary formation appears to be extraordinarily difficult through normal processes, might this alternative pathway occasionally succeed? Could the right combination of density, temperature, and composition rarely but eventually lead to the direct formation of planetary mass objects in interstellar or even intergalactic space? If so, then the universe might gradually accumulate a small population of these rogue planets, drifting through the vast emptiness between stars. These would be dark, cold worlds, with no star to warm them, relying only on internal heat from formation and perhaps radioactive decay to maintain any temperature above the frigid background of space. They would be extraordinarily difficult to detect, visible perhaps only through gravitational microlensing when they happen to pass in front of distant stars. But again, they would be planets, solid or gaseous bodies of planetary mass, existing independently in space. Their occasional formation over the vast spans of cosmic time would slowly increase the planetary population from one to perhaps a few dozen or few hundred scattered across the universe, maintaining Earth's status as extraordinarily rare but not absolutely unique. A third possibility involves the transformation of existing astronomical objects into planet-like bodies through processes not involving traditional planet formation. For instance, under certain conditions, white dwarf stars might crystallize as they cool, effectively becoming enormous diamond or oxygen neon magnesium crystal spheres. While technically stellar remnants rather than true planets, these objects would share certain characteristics with planets, being solid bodies composed of elements heavier than hydrogen and helium. Similarly, neutron stars, the ultra-dense remnants of massive stellar explosions, represent another class of objects that, while not planets in the traditional sense, are solid bodies with surfaces and internal structures, albeit under conditions of density and gravity far beyond anything found on actual planets. As the universe ages and more stars die, the population of these planet-adjacent objects would increase. In the far future of our solitary Earth universe, these various exotic objects, from crystallized white dwarfs to neutron stars to directly collapsed rogue planets, might collectively outnumber the single traditional planet, Earth. This would create a cosmic environment where planetary or quasi-planetary bodies are still extraordinarily rare compared to stars and galaxies, but no longer limited to a singular example. Let us also consider more exotic possibilities involving cosmic evolution over truly vast timescales. The universe continues to evolve, with stars forming, living and dying, galaxies merging, and large-scale structures developing. Over periods of billions or trillions of years, conditions throughout the cosmos change in ways that might alter the probability of planetary formation. For instance, each generation of stars enriches the interstellar medium with heavier elements produced through nuclear fusion and supernova explosions. This process, called chemical evolution, gradually increases the proportion of elements like carbon, oxygen, silicon, and iron, the building blocks of rocky planets like Earth. In our universe, this enrichment has made planetary formation more likely over time, with older stars less likely to host planets than younger ones due to the lower availability of these planetary building blocks in the early universe. In our solitary Earth universe, if planetary formation is extraordinarily difficult, but not absolutely impossible, then this gradual enrichment might eventually create conditions where new planets can form around newly born stars. Perhaps Earth formed as the result of some incredibly rare conjunction of factors, a 1 in a trillion cosmic accident that occurred early in the universe's history. But as the cosmos ages and grows richer in heavy elements, the probability, while still small, might increase enough that additional planets eventually form. If this were the case, then Earth's status as the only planet would be temporary, though perhaps lasting for billions or even trillions of years. Eventually, as new stars form from increasingly metal-rich nebulae, some might host their own planets, creating new solar systems that break Earth's long cosmic isolation. These would be genuine planets in the traditional sense, worlds orbiting active stars, potentially with atmospheres, geologies, and even the possibility of life. Another possibility involves rare cosmic events, creating conditions favorable for planet formation. For instance, when neutron stars merge, they eject neutron-rich material that undergoes rapid nuclear reactions, creating many of the heaviest elements in the periodic table. These merger events effectively seed their surroundings with concentrated packets of planetary building blocks. In a universe where traditional planetary formation is extraordinarily difficult, might these rare but enriching events occasionally create local conditions where planets can form? If so, then each neutron star merger might have some small probability of eventually leading to planetary formation in its vicinity, gradually increasing the cosmic planetary population over vast timescales. Let us also consider the possibility of planets entering our universe from elsewhere, if such an elsewhere exists. Some cosmological models propose the existence of a multiverse, where our universe is one of many, each perhaps with different physical laws or initial conditions. Other models suggest the possibility of bubble universes that might occasionally interact or even merge. While highly speculative, these models raise the possibility that in the far future, our solitary Earth universe might come into contact with another realm where planets are more common. If some form of transit between these cosmic domains were possible, planets from elsewhere might enter our universe, breaking Earth's isolation not through new formation, but through cosmic immigration. A less exotic but still intriguing possibility involves the potential discovery that apparent stars or other celestial objects are actually planets in disguise. Throughout astronomical history, advances in observational capability have repeatedly revealed that objects believed to be of one type are actually of another. Nebulae, once thought to be gas clouds within our galaxy, were later recognized as distant galaxies in their own right. Sources of radio emission initially classified as stars were later identified as quasars, the active cores of distant galaxies. Might future advances in astronomy reveal that some objects currently classified as small stars, brown dwarfs, or other celestial bodies are actually planetary in nature? If so, then Earth's status as the only planet might end not through the formation of new planets or the arrival of planets from elsewhere, but through the reclassification of existing objects as more is learned about their true nature. This possibility points to an important distinction between ontological uniqueness, Earth actually being the only planet in existence, and epistemological uniqueness, Earth being the only object known to be a planet based on current knowledge and classifications. The former might be permanent, while the latter could change with advances in understanding, even if no new planets actually form. Let us also consider the possibility of artificial planets, worlds constructed by advanced technology rather than formed through natural processes. If intelligent life on Earth eventually developed the capability for megascale engineering, it might choose to build planet-sized objects for various purposes, from habitation to resource utilization to scientific research. These constructed worlds would not be planets in the traditional sense of naturally formed celestial bodies, but they would share many characteristics with planets, potentially including solid surfaces, atmospheres, and even artificially maintained biospheres. Their creation would increase the population of planet-like objects in the universe, though through technological rather than natural means. Even more speculatively, if Earth life eventually developed the ability to travel to other stars, it might undertake the deliberate seeding of planets around those stars, using advanced technology to accomplish what natural processes in this universe seem unable to do. This would represent a form of directed panspermia in reverse, not spreading life to existing planets, but creating planets to potentially host life. Such technological planet creation, while far beyond current capabilities, might eventually become possible through methods like shepherding and compacting asteroid or comet-like bodies, harvesting material from stars, or manipulating matter at fundamental levels. These created worlds would represent a new category of planets, neither natural like Earth nor fully artificial like constructed habitats, but natural material deliberately organized into planetary form. Let us also consider how the longevity of planets might affect their cosmic population over time. Earth, while currently the only planet in our imagined universe, will not exist forever. As the Sun ages and eventually expands into a red giant billions of years from now, Earth's fate is uncertain. It might be engulfed and destroyed by the expanding Sun, or it might survive as a scorched, airless world orbiting the subsequent white dwarf. If other planets do form later in cosmic history, particularly around longer-lived stars than our Sun, they might continue to exist long after Earth has been destroyed or rendered unrecognizable. In this scenario, the universe would transition from having exactly one planet to having a few planets including Earth to having a few planets not including Earth. Earth's status as the first planet would remain, but its uniqueness as the only planet would be both temporary and unwitnessed in its final stages. The cosmic timeline of planetary existence in this scenario becomes particularly poignant. For billions of years, Earth exists as the sole planet, the only place in the universe where solid ground orbits a star, the only potential cradle for life. Then, perhaps trillions of years later, new planets finally emerge, just as Earth faces its final destruction from our aging Sun. The torch of planetary existence passes from the first world to its much-delayed successors, maintaining the presence of planets in the universe, but replacing the original with latecomers. This raises profound questions about the meaning of Earth's long cosmic solitude. If planets do eventually appear elsewhere, was Earth truly unique, or merely the first? Does being the only planet for billions of years, the only planet during the entirety of its biosphere's existence, make Earth special, even if it eventually gains cosmic companions? These questions have no objective answers, but would likely form central themes in the philosophy, religion, and science of a civilization that witnessed the end of Earth's planetary monopoly. Let us also consider the possibility that Earth's status as the only planet is temporary, not because new planets will form, but because Earth itself might eventually be destroyed or transformed beyond recognition. As discussed earlier, our Sun will eventually expand into a red giant, potentially engulfing Earth, or at least heating it to the point where its surface is molten and its atmosphere stripped away. Even if Earth survives this phase as a solid body, it would no longer be recognizable as the life-bearing world it once was. It would become a scorched, airless rock orbiting the white dwarf remnant of the Sun. Is such an object still meaningfully a planet in the sense that Earth is now? Or would the destruction of Earth's habitability effectively end its status as a true planet, leaving the universe once again without any planets at all? This question highlights the definitional complexities involved in determining what counts as a planet. If we define planets primarily by their physical characteristics as solid or gaseous bodies of a certain mass range orbiting stars, then Earth would remain a planet even after being rendered sterile by the Sun's evolution. But if our definition includes functional characteristics related to potential habitability or complex environmental systems, then the destruction of these features might indeed end Earth's status as a true planet. In this latter view, the universe begins with no planets, develops exactly one planet for a limited period measured in billions of years, and then returns to a planetless state for the remainder of cosmic history, potentially trillions or quadrillions of years. Earth's existence as a planet becomes a brief interlude in an otherwise consistent pattern of cosmic planetlessness. Let us also consider the possibility of planets forming through currently unknown processes that might become more common in the far future as cosmic conditions change. The universe continues to evolve, with potentially habitable stars like our Sun remaining active for many billions of years to come, followed by much longer periods dominated by red dwarfs, white dwarfs, neutron stars, and black holes. As the cosmos ages, new physical regimes emerge, with different temperature ranges, energy densities, and chemical compositions predominating. Processes that are virtually impossible under current cosmic conditions might become viable in these altered future states. Perhaps modes of planetary formation that cannot occur now will become possible in the distant cosmic future, leading to new planets unlike anything we can currently imagine. These far future planets might form through exotic mechanisms involving dark matter, which makes up about 85% of the matter in the universe, but currently interacts minimally with normal matter. Or they might involve processes related to the eventual evaporation of black holes through Hawking radiation, creating conditions unlike anything in the current cosmos. While highly speculative, these possibilities remind us that the universe's creative potential extends far beyond its current state and may manifest in unexpected ways over its vast future lifespan. Finally, let us consider what the discovery of new planets through any of these mechanisms would mean for the inhabitants of Earth or their descendants. After billions of years of cosmic solitude, the confirmation that other planets exist, whether naturally formed, artificially created, or arrived from elsewhere, would transform their understanding of their place in the universe. This revelation would challenge long-held assumptions about Earth's unique status, potentially triggering profound revisions in scientific theories, philosophical frameworks, and perhaps religious or cultural beliefs. The specific nature of these new planets, whether they bear any resemblance to Earth or are utterly alien in form and composition, would shape how this new knowledge is integrated into the collective worldview. If these new planets proved capable of supporting life, particularly if they already hosted indigenous organisms, the implications would be even more revolutionary. Earth would transition from being not just the only planet, but the only life-bearing world, to being one among a few biological outposts in an otherwise sterile cosmos. This might foster new forms of cosmic identity, based not on planetary uniqueness, but on biological kinship across different worlds. In a universe where planets are extraordinarily rare, the discovery of even one additional world would be a momentous event, potentially rivaling the greatest scientific revelations in significance. It would transform a universe of absolute planetary uniqueness into one of extreme planetary rarity, a subtle but philosophically profound shift in cosmic perspective. As we contemplate these possibilities, we are reminded that even in a universe where Earth begins as the only planet, the story of planetary existence may still have future chapters waiting to be written. The cosmos continues to evolve, to create, to transform itself over timescales that dwarf human experience, or even the lifespan of species and biospheres. What begins as a universe with one solitary world might not remain so forever, as new pathways to planetary formation emerge or existing celestial objects are transformed or reclassified. The question is not merely whether other planets might appear later, but what such an appearance would mean for our understanding of cosmic evolution, the prevalence of life, and Earth's place in the grand scheme of things. The answers remain speculative, but the questions themselves remind us that even in a universe of apparent cosmic solitude, the possibility of change, of new discoveries, of unexpected companions remains open. Perhaps one day, another world will enter the scene. Our journey through a cosmos containing only one planet is nearing its end. We have explored a universe where Earth stands utterly alone, the sole planetary body amid countless stars and galaxies. We have contemplated how such a world might form, how it might evolve without a moon or cosmic impacts, how life might emerge and develop in isolation, and how intelligent beings might make sense of their unique status. Now, as our meditation draws to a close, let us reflect on what this cosmic solitude means, on the profound implications of a universe of one. Imagine once more our pale blue sphere suspended in darkness, Around it, no Mars glows red in the evening sky. No brilliant Venus heralds the dawn. No majestic Jupiter with its retinue of moons breaks the monotony of the stellar backdrop. Just Earth, alone in the void, orbiting an ordinary star in an ordinary galaxy, yet extraordinary in its singular existence. This solitude grants Earth a dual status in the cosmic hierarchy. On one hand, it is utterly insignificant in the grand scale of things, a tiny speck orbiting one star among billions in one galaxy, among billions. Its matter constitutes the merest fraction of the universe's substance, its lifespan but a moment in cosmic time. In these terms, Earth is cosmically trivial, a rounding error in the universe's accounting. Yet, on the other hand, Earth possesses absolute significance as the only world of its kind, the only place where matter has gathered into a planetary body, the only solid sphere orbiting a star in the entire cosmos, the only potential cradle for life and consciousness. In these terms, Earth is cosmically extraordinary, unique in a way nothing else can claim. This tension between insignificance and uniqueness creates a philosophical paradox that beings on such a world would grapple with throughout their intellectual history. Are they special, chosen, intended by cosmic forces or divine will to exist as the universe's sole planetary inhabitants? Or are they an accident, the result of chance events so improbable they occurred exactly once in the entire history of existence? Neither answer fits comfortably with the evidence, leaving a perpetual mystery at the heart of their cosmic understanding. The night sky in this universe tells a story different from our own. The stars still shine, still map the seasons and guide navigation, still inspire wonder at their distant fires, but they reveal a cosmic landscape fundamentally unlike the one we observe. A universe where planets are not merely rare, but unique to our orbit, where solid worlds do not circle other suns, where Earth stands alone in its fundamental nature. This cosmic message, read in the darkness between the stars, shapes everything about life on our solitary Earth. It influences the emergence and evolution of life, developing without the lunar rhythms that pace our tidal zones, without the asteroid impacts that punctuate our evolutionary history. It transforms human culture, or its equivalent, with mythologies, sciences, and philosophies reflecting this cosmic isolation. It alters the trajectory of technology and exploration, with no other worlds to visit or study up close. Perhaps most profoundly, it shapes how conscious beings understand their place in the cosmos. In our actual universe, we have gradually recognized our non-central, non-special status. We orbit an ordinary star in the outskirts of an ordinary galaxy, one of countless worlds circling countless suns. This realization has been humbling, but also connecting, placing us within a cosmic community of worlds, bound by common physical laws and perhaps common evolutionary principles. But for beings on our solitary Earth, this recognition would be only half complete. They would still discover their star to be ordinary, their galaxy one among billions, but they would also confirm, with increasing certainty as their astronomical capabilities advanced, that their world is genuinely unique, the only planet in existence. This knowledge would deny them both the comfort of cosmic specialness and the perspective of cosmic mediocrity, leaving them in a philosophical middle ground where they are simultaneously insignificant and exceptional. The ethical implications of this dual status would likely shape their civilization profoundly. The knowledge that their world is the only platform for life and consciousness in the entire universe might foster a deep sense of responsibility for its preservation, not merely for their own benefit or even for future generations of their kind, but for the continuation of the only biosphere that exists or could exist anywhere in the cosmos. This responsibility might be experienced as a great burden, a cosmic duty they never asked for but cannot escape. Or it might be seen as a profound privilege, the opportunity to serve as caretakers for the universe's sole experiment in planetary existence and biological complexity. Most likely, it would be felt as both, creating a complex relationship with their world and their role as its inhabitants. The scientific enterprise on such a world would develop along unique lines. Without other planets to study directly, their understanding of planetary processes would come solely from examining Earth itself and theorizing about alternatives. Their astronomy would focus intensely on stars, galaxies, and cosmic structure, perhaps advancing more rapidly in these areas than ours. but lacking the grounding comparative perspective that other planets provide. Their search for answers about their world's unique status would drive scientific innovation, but also create persistent mysteries. Why did planetary formation occur exactly once? What confluence of factors led to Earth's existence, while preventing the formation of any other planets? These questions might never find satisfactory answers, remaining as scientific puzzles that hint at the limits of understanding in a universe where some phenomena have no comparatives to study. For any technological civilization arising on this world, the question of long-term survival would take on special poignancy. In our universe, the possibility exists, at least theoretically, of expanding beyond Earth to other worlds if our home planet becomes uninhabitable. Even if practical challenges make this difficult, the presence of other planets offers at least the concept of alternative habitats for life. In a universe with only Earth, no such alternatives exist. The knowledge that their world is not merely their current home, but the only possible home for life anywhere, would likely intensify efforts to ensure its long-term habitability. Yet it would also force a confrontation with the ultimate limitations imposed by stellar evolution. As their sun eventually ages toward its red giant phase billions of years in the future, they would face the certainty that not just their species but all life in the universe would end unless they could create entirely artificial habitats, or somehow alter their star's evolution. This existential pressure, the knowledge that they are the universe's only chance for the continuation of life and consciousness, might drive technological development in unique directions. It might foster innovation in environmental preservation, in space habitat construction, in extreme adaptation to changing conditions. It might even drive efforts to create new planets artificially, to build solid worlds around other stars using advanced technology to accomplish what natural processes in their universe could not. The spiritual and philosophical perspectives emerging on such a world would likely reflect its unique cosmic context. Traditional religious frameworks often place humanity and Earth at the center of creation, with special divine attention and purpose. The discovery of countless other galaxies has challenged these perspectives in our world, suggesting either a creator with concerns far broader than one planet or natural processes operating without special intention toward Earth. For beings on our solitary Earth, this tension would take a different form. Their world would be demonstrably unique as the only planet, potentially reinforcing notions of special creation or purpose. Yet it would also be demonstrably tiny and brief against the vast backdrop of cosmic time and space, potentially reinforcing naturalistic perspectives that see no inherent meaning in existence. Neither traditional religious centrality nor complete cosmic insignificance would fully align with their observed reality. This might foster spiritual innovations unlike those in our traditions, perhaps perspectives that see their world as simultaneously special and ordinary, central and peripheral, intended and accidental. The spiritual questions would not be easily resolved through either traditional faith or materialist rejection, but might require new conceptual frameworks that embrace this paradoxical cosmic positioning. The psychological experience of existence on such a world would likely differ from our own in subtle but important ways. The knowledge of their cosmic uniqueness might foster both a profound sense of isolation and a deep appreciation for the extraordinary nature of their existence. They might feel both more alone and more special than we do, creating a complex emotional relationship with the cosmos that shapes art, literature, music, and other cultural expressions. The very concept of home would take on different dimensions. Earth would not be merely their current dwelling place, but the only possible planetary home for any beings anywhere ever. This might create a deeper sense of belonging to their world, a stronger identification with Earth as not one planet among many, but the only planetary body in existence. The psychological boundaries between self, species, world, and cosmos might blur in unique ways, fostering perspectives on identity that differ from those in our more populated universe. As their scientific understanding advanced and their technological capabilities grew, they might eventually reach beyond their solitary world, not to visit other planets, but to study the stars, galaxies, and broader cosmic structures directly. Space stations, orbital habitats, and interstellar probes might extend their presence beyond Earth, creating artificial environments where none existed naturally. These constructions would not be stepping stones to other worlds, as they might be in our universe, but extensions of the only world, Earth, reaching tentatively into the void. The contrast between their solid, life-sustaining planet and the emptiness surrounding it would be starker without the conceptual middle ground of other planets, potentially creating a sharper division in their thinking between Earth and everything else, between the planetary and the non-planetary, between home and the inhospitable beyond. As they contemplated the far future, they would face the knowledge that their world, the only planet in existence, would not last forever. The Sun's eventual evolution would render Earth uninhabitable, forcing a choice between extinction and the creation of entirely artificial habitats untethered to any planet. This looming cosmic deadline, billions of years distant but ultimately unavoidable, might influence their long-term thinking, their sense of purpose, and their technological development in ways different from our own, where the theoretical possibility of other planetary homes exists. The art and literature emerging from such a civilization would likely reflect these unique cosmic circumstances. Themes of isolation and uniqueness, of responsibility and cosmic purpose, of the tension between insignificance and exceptionalism would find expression in their creative works. Their mythology, even as it evolved into more scientific understandings, might retain a sense of Earth's special status, the only solid ground in an otherwise fluid and gaseous universe. Their visual art might emphasize the contrast between Earth's solidity and the vast emptiness surrounding it, between the rich complexity of their biosphere and the comparative simplicity of stars and interstellar gas. Their music might explore themes of singularity and multiplicity, of the one amid the many, of unique voices calling into cosmic silence. Their literature might grapple with the philosophical implications of being the universe's only planetary inhabitants, the only conscious beings contemplating a cosmos that produced exactly one world capable of supporting such contemplation. Even their language might evolve differently, with concepts and categories shaped by their unique cosmic context. The very idea of world or planet would refer to exactly one thing, rather than a class of objects. This linguistic singularity might influence how they think about categories, universals, and the relationship between the unique and the common, in ways that differ from our conceptual frameworks. As we imagine this solitary Earth and the beings that might inhabit it, we gain perspective on our own cosmic context. We recognize how profoundly our thinking has been shaped by the existence of other planets, by the knowledge that Earth is one among many, that our solar system is one among billions, that we occupy one instance of a common cosmic phenomenon rather than a unique occurrence. This perspective has both humbled and expanded our conception of ourselves. It has helped us see Earth not as the center of creation, but as one habitat among potentially many, one experiment in the evolution of matter and energy among countless others throughout the cosmos. It has connected us to a broader community of worlds, united by common physical laws and perhaps common developmental pathways. But it has also perhaps diminished our sense of responsibility for our planetary home. The theoretical possibility of other habitable worlds, the concept that life might exist elsewhere even if Earth becomes uninhabitable, might unconsciously reduce our commitment to preserving this world's habitability. The beings of our solitary Earth would face no such psychological escape. They would know with absolute certainty that their world is not merely their current home, but the only possible home for conscious life anywhere in the universe. This absolute responsibility might foster a deeper environmental ethic than our own, a more profound commitment to preserving the only biosphere in existence. It might create a civilization less willing to risk its planet's long-term habitability for short-term gain, more invested in maintaining the cosmic miracle of the only world where matter gathered into a life-sustaining sphere. Or it might, paradoxically, foster fatalism in the face of cosmic isolation. If their world is utterly unique, perhaps its existence is so improbable that its long-term preservation is unlikely regardless of their efforts. This perspective might undermine environmental responsibility rather than enhancing it, leading to a focus on immediate concerns rather than long-term planetary stewardship. The tension between these responses, between heightened responsibility and resignation to cosmic rarity, would likely shape the civilization's development, creating internal dialogues and conflicts that differ from those in our own society. The specific path they followed would depend on countless cultural, historical, and psychological factors, but would always unfold in dialogue with the knowledge of their world's absolute uniqueness. As our meditation on this solitary Earth concludes, we are left with a deeper appreciation for the complex cosmic context of our own world. Neither absolutely unique nor merely ordinary, Earth exists as one planet among many, rare perhaps in harboring complex life, but common in its basic nature as a solid world orbiting a star. This middle position, neither cosmically special nor utterly insignificant, creates its own philosophical challenges and opportunities, its own framework for understanding our place in the universe. The beings of our imagined solitary Earth would face a different set of questions, a different relationship with the cosmos, a different understanding of their significance. Their journey would be one of reconciling absolute uniqueness with relative insignificance, of making meaning in a universe where they are simultaneously the only planetary inhabitants and a tiny, brief phenomenon in an almost incomprehensibly vast cosmos. Their story reminds us that cosmic context matters, that how we understand our place in the universe shapes how we think about meaning, purpose, responsibility, and identity. It invites us to appreciate the particular context of our own existence, neither as the center of creation nor as merely one world among countless identical others, but as one instance of planetary existence in a cosmos where such existence appears to be common but not universal, significant but not unique. A universe with only Earth is a quiet one, a still one, but not an empty one. It is a universe that contains, on one small world orbiting one ordinary star, the extraordinary emergence of complexity, life, and consciousness. A universe where matter has organized itself, in one location among billions of galaxies, into beings capable of contemplating their own existence and the vast cosmos that surrounds them. It is a universe that listens, that observes itself through the eyes of the creatures of its only planet, that achieves self-awareness through the thoughts of beings evolved on the only solid world it contains. In this way, the entire cosmos achieves a kind of consciousness through its singular planetary offspring, making the existence of this one world far more significant than its physical proportions might suggest. And perhaps it is a universe that dreams of more, that contains within its fundamental laws the possibility, however remote, of additional planets emerging in the far future. That holds the potential for its sole planetary inhabitants to create new worlds through advanced technology, extending the phenomenon of solid, complex spheres orbiting stars beyond the original solitary instance. This dream of more, this potential for expansion beyond the initial singularity, reminds us that even a universe of one is not static or final. It continues to evolve, to create, to transform itself over timescales that dwarf human experience, or even the lifespan of species and biospheres. What begins as a universe with one solitary world might not remain so forever, as new pathways to planetary existence emerge, or existing celestial objects are transformed by natural processes or technological intervention. But for now, in the present moment of our meditation, we contemplate this universe of one. We appreciate the quiet beauty of a cosmos where Earth floats alone, the only island of solid matter in an ocean of stars and void. We reflect on what such uniqueness would mean for the evolution of life, for the development of intelligence, for the philosophical understanding of beings who found themselves the only planetary inhabitants in existence. And in this reflection, we gain a deeper appreciation for our actual cosmic context, for the complex interplay between uniqueness and commonality that defines Earth's true place in the universe. We are not alone as a planetary body, but we may be rare as a cradle of complex life. We are not unique in our basic nature, but we may be exceptional in the particular path our evolution has taken. We are not the center of creation, but neither are we merely one identical instance among countless others. This nuanced understanding of our cosmic position, neither absolutely unique nor utterly ordinary, creates its own philosophical richness, its own framework for contemplating meaning and purpose in a universe where we are simultaneously special and typical, rare and common, central and peripheral. It invites us to create meaning that acknowledges both our connection to a broader community of worlds and our potential uniqueness as bearers of consciousness in our local cosmic neighborhood. As we return from our thought experiment, from our meditation on a universe with only Earth, We bring with us a deeper appreciation for the actual universe we inhabit, with its billions of galaxies, its countless stars, its multitude of planets, and, on at least one world, its emergence of life and consciousness capable of contemplating it all. A universe with only Earth is a compelling thought experiment, a window into alternative cosmic possibilities, a mirror that reflects our own existence in new and revealing ways. But the universe we actually inhabit, with its rich diversity of worlds and its possibility of multiple cradles for life and thought, offers its own profound beauty and significance. It invites us to see ourselves as both unique and connected, both special and ordinary, both responsible for our planetary home and potentially part of a broader cosmic community. Sleep now, beneath a sky dotted with planets, on a world that is rare but not alone. In a universe that contains not just us, but perhaps others who also look up and wonder.